ఆడ ఆపిందట సెకండ్ గేట్ కాడ ఫోన్ చేస్తాను.
Can we start? Are all of you guys well settled? Yeah? You had a good evening on this very nice campus? I enjoyed the campus. It's very good. Excellent. So, before I get started, just one housekeeping announcement. We are going to switch these two. Yeah? I hope you don't mind. So, I will do the second post-treatment module also before lunch, and then we'll break for lunch, and I've requested this change with Dr. Manjya so that I can see some nice departments on this campus in the afternoon, right? I'll have more time to do that. Okay. I must also say that some of these modules are not very exciting for me because there is not so much research involved. So, I may not take so much time talking about feedstock because I am talking about it more to just relate information. There's nothing very innovative that happens in feedstock, but you should know what is the typical feedstock, what you should be careful about, how it's made. Yeah, but maybe I'll take slightly less time for this and more time for that because I find that very exciting. Post-treatment, right? So, I hope that is also okay with you. But of course, even if I speak little bit less, if there are any questions, I'm of course happy to answer. Let's start with feedstock for metal AM. As you know, that is our focus. We don't talk about other things so much. Yeah. So, what are the two main feedstock? What two kinds of feedstock do we have for AM? Wire and powder, correct? So, let's talk about both of those little bit. Let me introduce some of my colleagues here. Magnus is a postdoc, now a lecturer who works on different aspects of additive manufacturing, but mostly on titanium. Peter is from Sandvik. They are one of the biggest powder suppliers for AM. They have their own additive manufacturing cell department, and then they participate in many of our projects because whenever people make new feedstock, they need someone to test it and optimize parameters for it and publish using that feedstock so that they get better known. So, Sandvik is one such partner. Ibrahim, he is a Iranian student who did his PhD with us, and now he works in the R&D department of ITW. They are one of the biggest suppliers of wires, right? So, I have taken some help from them in preparing this talk. let's start, we already spoke about that. We'll talk a little bit about powders, a little bit about wire, more about powder than wire, because historically people have been using the same wires that they use for welding and cladding. There's nothing different there. Although it could change, right? Because AM is such a new field, right now people use what is available, even with standards. And that's why I find the post-treatment part very interesting, because uh, there have been standards available for materials that are traditionally manufactured for, let's say, heat treatment, and people use the same standards even now. They are specified as standards for AM, but we have shown, one of my earlier PhD students, that you need not use the same heat treatment, for example. What you can do for AM can be very different from what is traditionally done in case of cast or forged material, right? So that's important to know. Let's talk about powders in general, and what are the main metal powder consolidation processes. I don't know how many of you have heard of near net shape by hot isostatic pressing. Yeah, in one sense it's a very old technology, but very prevalent in the industry. Yeah, many of the powder metallurgy parts are made by hipping even now, or sometimes they use also cold isostatic pressing and that kind of stuff, or sintering. But when it comes to near net shape, this is one of the main consolidation processes in vogue, but we will not talk about that, because I don't believe that really qualifies as additive manufacturing. So we take that out. Yeah. Similarly, metal injection molding, also very popular when it comes to consolidating powders. So this is just for information. It just doesn't fit in the rest of the things we talk about. Binder jetting, DED, PBF. We spoke about all of these, and today we will talk about powders in the context of at least these two. Yeah, the directed energy deposition and powder bed fusion, right? I will quickly run through, not spend so much time. If you have questions, we will spend time, but otherwise not so much. We will talk about what are the prominent methods by which powders are produced, and how, based on what is the method, how the powder properties can be different. How many of you think that these are important properties for AM? Which of these is important? Which of these, according to you, is not important? Yeah, let's go one by one. Sphericity or shape, is it important? Yeah, why is it important? Okay. All right. Do you agree with what he said, or you have some other input? Yeah. So people generally believe that you need spherical powders because flowability is better, and because you can perhaps rake it well. That's what you meant, I think, that raking is better. I will accept that. I will not argue about it at the moment. But I must tell you that powder bed is a little bit different from DD, because you're raking and stuff, right? So, but I must tell you that almost all of, let's say, thermal spray, right? More than half of the thermal spray powders, even more, are not spherical. Yeah, they are sintered and crushed. Yeah, therefore angular. They flow very well. Yeah, so there are some things in our mind which are historical sometimes, but today we get really good powder feeders, right? we are able to feed powders which are as fine as 3 to 5 microns even, right, which earlier was not possible even with spherical powders. So, today powder feeders are very good, but by and large what you are saying is right. Yeah, spherical powders are better, but you must also know that it is not absolutely necessary, right. There is flowability in angular powders as well, which is not so bad. Yeah, but with powder bed, as we were briefly talking yesterday, at the moment everyone says spherical powder necessary, everyone believes spherical powder is necessary. So, we will assume that it is necessary, right, for the time being. Yeah. Size and size distribution, is that important? Why is that important? Why is size distribution important?
Separate size by size. The powder is not something it can separate. So the size by size is not that important. Because when we scrape it, everything gets settled well. Even the small powder gets into the gaps and gets into the correct place. So size and size is not much important.
Not much important. Who doesn't agree with what this gentleman is saying, that size and size distribution is not important? You disagree? Why?
If we have different sizes, we make it interior. We will get gaps between.
I will say one more time, you are all engineers. Please use the right terminology, right? If size is different, you get impurities. If you say impurities, I don't like, right? So, you may not get complete melting sometime. Yeah, that's what you mean, right? So, that's okay. Yeah, but you can't say impurities. Yeah, yeah. Phenomena of fusion. Yeah, correct. Absolutely correct. That's the right answer, right? Having said that, particle size distribution is inevitable. Yeah, it will be there, and I think that is what you were trying to tell, right? You cannot get mono-sized powders. Of course you can, but you have to give an arm and a leg to get that. It will be very expensive. If you say I want powders between 10 and 11 microns or something like that, it will be very expensive, right? So typically powders have a range. We spoke yesterday about 50 to 100 microns, 10 to 45 microns. So they have a range, and that is okay. You have to live with that for any process to be practically feasible, right? And what you said also is correct. There is a lot of work done on how a size distribution improves packing density, right? So, but that's a different story. We need not get into that right now. But I am happy you said that. For a BTech second year student, that's impressive. Yeah, that's pretty good. Yeah, powder morphology, yeah, we are for the moment assuming that you need spherical. Packing density, same point, right? And both of these eventually affect the bulk density of what you build. Yeah. You see all kinds of morphologies depending upon what manufacturing route you have adopted to make the powder, right? Once again, I'll go back to thermal spray. We use lot of these kind of powders as well. Yeah, still works quite well, right? But most of the AM crowd today uses these kind of powders. Yeah, because they're afraid. Yeah, we are afraid that any other powder will not work. Yeah. So, if you want to write a wish list for the kind of powders you want to buy today, here is some of the points that I was looking at on one of these websites. You want spherical shape to ensure good flow. You want particle size. It depends upon what method you are using, but let's say 50 to 100 microns. Particle size distribution should be tailored, right? I mean, if you're talking about packing density, that's not bad. If you have all of this size, you of course will not get such packing, but people say it should be tailored for the application. Nobody does that, right? Nobody does that kind of tailoring, because is just impractical. Imagine I am a powder supplier, right? Uh, I cannot begin to make different distributions in the powder for someone who is doing DED, someone who is doing uh, uh, powder bed fusion, someone who wants it for coating, someone who wants it for powder metallurgy part. So, the best thing they do is sieve and differentiate cut sizes, right? But beyond that, they don't do so much. But you do get, if you open any powder manufacturer's catalog, you will get many size distributions, right? Many different cuts, 5 to 15, 15 to 45, 45 to 90, more than 90, whatever, right? So depending upon what suits you best, there is a big choice to be made. Controlled chemical composition, yeah. This is where you must, who spoke about impurity, yeah. This is where you must take care of impurities, whether or not they're there, right? Controlled chemical composition. There is one aspect we will not get into here, but in some cases people expect elemental loss during processing, and therefore they want to correct that in the feedstock, right? There are many examples there. Yeah, if you expect elemental loss during processing, you have a little bit more of that element in the feedstock and assume that it will get, a little bit of it will get lost, right? So there are ways to tailor composition in that sense. Some of these powders, depending upon how they are made, also have some entrapped gas in them. What happens if there is entrapped gas in the powder? Yes, that leads eventually to porosity in your build, correct? So all of these are important things to consider. Potential problems, inclusions within the powder granules. Sometimes we spoke about entrapped. Yeah, all of these you should know. You should always insist on couple of things from the powder supplier. Yeah, insist on a chemical analysis always. Yeah, insist on a size analysis as well, right? Those two things you must always insist on from whoever the source of your powder is, right? We saw this yesterday, the range of materials that you can use in AM. This is an endless list. Yeah, it can go on and on. Right now we were, while I was walking, I was talking to Dr. Manjay about what one of his PhD student does with DED, and that is multi-material. Once you talk about multi-material, I mean, the field is just wide open, right? You can do almost anything. I have a PhD student myself who's working on multi-material DED, and we are trying in that case to do Inconel substrate with an M. Crawley and graded to yttria stabilized zirconia. So we are doing a metal ceramic functionally graded, right? So you can do anything. We have another project that we are discussing with GIAN Aerospace, where they want us to build copper along with stainless steel, or copper ideally with a nickel based superalloy, and we are absolutely struggling. Why are we struggling? Take this example, copper with nickel based superalloy. Why are we struggling, you think? Huh? Thermal conductivity, I don't think that we are struggling with that so much. Yeah, I mean, mostly that. We are struggling because the laser that we have been using for depositing the nickel based superalloys suddenly is inadequate when it comes to copper. So we are not okay with that laser for when it comes to copper. So we are shopping for a green or a blue laser at this point. So anyway, that was an aside, but important that you know, there's so many things you can do. For each of these you will need powder, and you need to find suitable sources for that, right? And I suspect that each of these would, if you went back to the previous slide, uh, how important all these issues are will sometimes depend upon which material you're talking about. Okay? Uh, for example, titanium will have completely different set of challenges compared to, let's say, something like stainless steel. This will be much more forgiving. Doesn't matter if it's something happens slightly with composition, but with titanium, nickel-based superalloys, yeah, your threshold is pretty stiff. Yeah, uh, some materials like this also are extremely difficult to deal with, but here you may want to revisit the size, right? So you cannot always talk about the same particle size. These are very high melting, correct? Extremely high melting materials. So you can't use the same particle size in a given process as you would use for maybe copper or stainless steel, right? You should be aware of that. Powder manufacturing methods. Oops. While that comes up, let's go around. How many powder production methods are you guys aware of? Name anything that comes to mind. Powder production. Ball mill, yeah. Will you get spherical powders by ball mill anytime in your life? Huh? No, right? But yeah, if you want to mechanically alloy powders, then ball milling is a good idea, but not for spherical powders. But yeah, now that this is up, yeah, if we assume that spherical powders is our target, right? Most often people use atomization techniques, right? There are different kinds of atomization. I have mentioned some here. Gas atomization, most popular, gives you the best quality of spherical powders. Not necessarily the cheapest, but best. Yeah. There is also plasma atomization, water atomization, lots of stuff there, right? What is atomization, you think? Simplest definition of atomization, anyone? Disintegration. Oh, yeah, okay.
Breaking down of the material to smallest possible size and smallest possible particles.
So at the you're making life very complicated. You are relating atomization to atoms. Yeah, that's not the case. Yeah. Yeah, that's what I'm saying. You're relating that to atoms. That, no, it's not that complicated. So usually, oh, is the problem with the projector or that cable, you think? But this is also turning off, looks like, or no? Or? Anyway, let's keep chatting. How many of you use powders in whatever you do? Uh, not talking to undergraduates so much. How many of you use powders in your research or whatever you are presently doing? No, you use powders. Okay. What kind of powders do you use? Spherical. And for what application?
Sir, HGMs.
By DED.
Yes, sir.
Yeah. Okay. So you use stainless steel for DED. So when you get a powder, what do you characterize it for? Because that's something we are going to talk about here. What are the important characteristics of the powder? So what do you do with the powders once you receive from a supplier?
Sir, we do SMT, sir, to
Yeah.
check the shape size.
You will do STM, okay? For shape and size, all right. What else?
Particle distribution size.
Yeah. SCM is too much, no, for just shape and size, but yeah. Okay, you do that. Yeah.
XRD you do, sir.
You will do XRD, okay. What will you do XRD for?
Elemental mapping. You know the structure, type of the structure first.
XRD for elemental mapping.
EDS.
EDS.
One at a time. XRD for elemental mapping.
No, sir, means not for elemental mapping basically. Basically, we are determining the lattice parameter, crystallite size.
Yeah, I mean, in a more broader sense, I will do XRD to find the phase constant. Yeah, what phases are present in my powder. Someone said EDS also. Why do you do EDS? Yeah. Okay. And both EDS and XRD in some way tell you what apart from what you need in the powder is also present in the powder. So kind of impurity. Suddenly there is some oxide or some carbide or something you completely did not expect. Yeah. If something like that is present, you will get it from XRD or an EDS. Yeah. Which is attached to the SCM. Right? That's very good. How about what size of powders do you get for your DED? 50 to 150. Yeah. Wow, that's big distribution. Yeah. Who else raised their hands for powder? Yeah. What do you use it for? 50 to 105. Which powder? Same. So why do you use 50 to 150 and why do you use 50 to 105? But she is also using for DED. But you can use different particle sizes. That's the point. It doesn't matter. Yeah. So you can use both. Okay now. What is the problem? Yeah, technology. Always, even in our place, we have a project meeting. More than the problems with the project, we have problems with the projector. No? So, and always hard to solve. Sometimes someone can't connect on Teams or Zoom, some crazy problem like that. But these are global. These are not Warangal. I showed you that. Yeah. But let's talk about atomization, right? I was talking about this. So all of these atomization techniques are the most popular to make spherical powders. If you don't want spherical, there are other ways, but I've stayed out of that. Out of all these, gas atomization is the most popular, especially for powders that are used today for additive, and it involves three major steps. One is melting, the second is atomization, and the third is eventually once you get a product, you want to size it. You want to get rid of the fines, you want to get rid of the coarse powders, right? So these are the three main steps, right? So when it comes, So when it comes to gas atomization, you actually need to find a way to melt your feedstock, right? You could do it in different ways, right? You could have the charge initially in the form of an ingot. You could, if you are making complicated powders, you can put all these different powders together, make an ingot out of that, and then melt and atomize, right? And so you essentially atomize. In this case, atomization means fragmentation. Yeah, you fragment a molten droplet, not take it to the level where you can't divide it anymore and all that. That's too far, right? Atomization is fragmentation. So the molten stream is then fragmented, and then you cool it, right, very quickly, so that these droplets solidify really quick, and you get spherical powders. Each droplet converts into a spherical particle. That is broadly the idea in all atomization techniques, right? So the changes may really happen in how you are melting it, right? In this particular case, this is equipped with a furnace, as you can see. So the melting happens under vacuum, so that there is no oxygen pickup, etc. And then these atomized droplets that are formed because of a high pressure gas that is used for atomization, these then solidify in flight to get your individual powder particles, right? As you can imagine, these would have a very varied size distribution. Yeah, so then there is of course a collection chamber, right? So these are collected and sometimes separated using a cyclone to some extent, and then finally sieved, so that you get the kind of size cut that you require. The reason people prefer gas atomization is that it's a very clean process. You do it in vacuum. You're essentially melting a charge and resolidifying the atomized molten stream. So there is not much opportunity for any contaminants to come in, right? And so cleanliness is a big thing. Even homogeneity from a chemistry standpoint is assured, because you're just melting that stream and solidifying that. So there is no in situ reaction involved or any such thing. So you get a very homogeneous microstructure as well because of the rapid solidification. Yeah, and there are some different variants of this gas atomization, but most of the differences essentially come there, right? How do you melt this? All the difference happens there. Just like with thermal spray, as I will talk, the fundamental of how coatings form is the same. What kind of heat source you use is different. Somewhat similar here. All the differences kind of reside there, but otherwise you do get atomized droplets which rapidly solidify, cool to form powders, right? Here in vacuum induction melting gas atomization, as the name suggests, this is equipped with vacuum at the top, and of course this vacuum during melting kind of ensures that it is clean. There is inert gas that is used for quenching the molten stream. So yeah, you have different variants of that. I don't want to get too much into detail, but all of them essentially try to do the same, right? Melt the feedstock. I mean, feedstock in this sense is the ingot or whatever of the same chemistry as the powder that you need, and then use an inert or inert environment to collect the powder that you desire, right? You can also do water atomization instead of gas. Yeah, use water jets like these to quench, right? This also works very well so long as water doesn't react. So when the materials that you are producing are non-reactive. Water is frequently used. It is much cooler. It gives higher cooling rates as well, right? So, how many of you have seen powder in SEM? You have seen powder in SEM? You told me you are looking at your characterizing your powder in SEM for size, or somebody else is doing for you.
No, sir, I just told theory.
Oh, just the theory. Okay. Who's looked at a powder under an SEM so far? Yeah, you and you. So how do you take a powder specimen under an SEM? Can you please tell? Little bit louder so that they should hear you.
Take a sample of a powder from the raw material tip as a piece of paper and observed under the microscope. It has time, whether metallic or non-metallic, we have to find it out, and then we have to paste it on the carbon tape. After that, we have to do the coating.
You said you take it on a piece of paper and see it under the SEM. Really, you do that?
No, sir. So in a tube we have to first store it, sir. In a small tube.
Whether metallic or non-metallic.
Louder. I like his answer because that's how we do it. Yeah.
Actually, we have to take the powder. First, we have to identify whether the powder is metallic or non-metallic. After that, if it is non-metallic, means we have to go for the coating.
What coating?
Normal sputtering coating.
Yeah. Mm.
Whether gold or otherwise platinum, we can use that.
Mm.
Or directly, it is metallic, means directly we can paste it on the carbon tape. After that, we have to use the dry hair in order to fully disperse the particles throughout the carbon tape. After that, we have to place it on the SEM machine. Based on the what is the electron we are going to use, whether you are going to use 15 kV or otherwise 10 kV or 20 kV. Based on that, we have to perform it.
Oh, I have to go beyond coffee for you. Yeah, excellent answer, man. Very good. Did you hear everything that he said? Yeah. So that's how you test a powder under an SEM. Yeah. And how do you do elemental analysis? Right. There are so many elements in the periodic table. What do you do? Do you have an auto detector, or you tell, okay, I want to look for nickel, I want to look for chromium?
Actually, we are using Oxford instruments.
Yeah.
EDX will be the Oxford instrument. In that, directly it will be directly it will be show the elements based on what is our requirement. For example, if we are done coating, means automatically platinum will also be visible or gold will also be visible in the EDX. So we have to remove that one. Based on that requirement, we have to take that one.
Very good. Excellent. Yeah. Nice. So all of you are now experts in SEM characterization of powders for AM. Yeah. But good answer. We should talk during tea break. I'm scared if you take it on a piece of paper. I'm very scared. I'm scared for your SEM more than anything else. Yeah. So I think we are losing a little bit of time here. So yeah, long story short, all of them do almost the same thing. Two things can vary. How are you melting the material? How are you cooling the material? Those are the two things that vary, right? Mostly. Here people use a plasma for atomization, and then you can cool again with these plasma torches are very high power. right? But this was one of the more innovative ways to do that. Uh, you will also come across something called prep powders. How many of you have heard of prep? Yeah, plasma rotating electrode. Yeah, so that's another way of producing these powders, right? So let's keep, oops, am I going in the wrong direction or? Right. Let's talk about. So you have melted the powder. You have rapidly solidified. You have the powder collected now, right? Which has a very wide size range. Then there are two ways to classify it in the size range that you want, right? Someone wants 50 to 105. Someone else wants 50 to 150, right? So there are ways to classify it. There are two methods. Sieving is the most popular because then you have lot more control over what lower size you want to cut off and what upper size you want to limit it to. Some people also use air classification, right? So for sieving, you normally use it for particles kind of coarser than 10-15 microns, and it has much higher productivity and throughput compared to air classification. And since you are essentially like a chalni type, right? You're using the same thing, so you can very easily get the size ranges that you desire, right? Air classification, yeah. Here 10 to 15 microns is usually the upper size limit rather than the lower size limit, correct? I was trying to get here already with the particle size distribution. There are many ways to do particle size distribution. We will not get into that analysis here, but it's important that for each process that you are targeting and for each material, you should be aware of what particle size distribution is suitable so that you don't get as someone mentioned, partial melting and therefore heterogeneity in your build, right? I will put a big star against this. So all equipment manufacturers will give recommendations for particle size distributions that are applicable. They will also give recommendation for who you should buy the powder from. Yeah, that recommendation will also come, right? But it is eventually left to our judgment what to do, where to buy these from. Yeah, characteristics, we touched upon this little bit. What are the important characteristics? The one I heard most times is flowability, and that is true, right? I think one of the key characteristics is flowability, which is governed by shape, etc. Generally very fine powders, and when you say fine, you're talking about really fine, yeah, which are not in the regime of AM, right? If you're talking about these days smaller than 10 microns, I think this limit has gone down a little bit, but generally very fine powders behave like talcum powder, right? Little bit. They have too many van der Waals forces or surface effects that tend for them to agglomerate, and therefore those don't flow very well, right? Sometimes density of the material also affects flowability. If the alloy has a higher density, it will flow faster. But imagine that I am mechanically blending two powders. Do you see a problem? If I have mechanically blended powders, right? Or just mix two powders. I am doing functionally graded in DED. I want to do whatever, stainless steel and copper. Yeah. So I've used stainless steel and copper by DED or whatever. Yeah. Both are spherical powders. I have mixed them. Yeah. 90-10, 80-20, 70-30. Do you see a problem because of this? So what I'm looking for the right word. What will happen? Should be low is not your choice, right? If you want to do functionally grading with A and B, you have to live with whatever the density of A and B is, right? That choice you don't have, yeah? But what should you be aware of? You should be aware of segregation, correct? If you are feeding both of them and they are not milled in that sense, but they are just put together, you can get segregation because of differential flowability of each, right, due to density differences. So that's something you must be careful about. In some cases, I don't know, maybe Warangal is a good place, not much humidity in the environment, I hope, yeah. But otherwise, there is often a recommendation that you dry the powder before using, yeah. If you expect that there could be humidity and that can affect flowability or at least lead to unreliable uniform flow, right? So we do this a lot in Sweden sometimes, just dry the powder before we use, right? So don't want to talk about this so much, but I hope this is my last slide. I'm tired of feedstock. I don't like it so much. Yeah. So I think you will see it in your notes, but desirable powder qualities, spherical, no satellites. I strictly don't believe in this. It's okay with satellites. If you know how to deal with them, you can still get very good builds. But this is what today's specification is, right? No satellites, no internal porosity, that's correct. Yeah, few surface pores, because all of these kind of lead to incorporation of pores or defects in your build, right? Narrow size distribution also good porosity, right? So, and I've just put down here how you will characterize these powders. We spoke a little bit about morphology, SCM, etc., porosity. There are different ways to do that. You can, like this gentleman said, you collect it on a carbon tape to look at morphology. You can also mount the powder, yeah, and then look at the cross section to see if there are like particle polishing, and then look at it under the SCM, right, to see if there are pores, etc. There are for flowability, there are very simple devices, right, like a Hall flow meter, where you kind of typically look at how much time does it take for 50 grams of powder to flow, or something like that, right? So there are measures of that, and yeah, little bit on handling, yeah. Surface pores are desirable. Yeah, so desirable is few or no surface pores. Yes, so, sorry if it is interpreted the other way. I'm not saying few surface pores are desirable. Yeah, desirable is that there should be few or no surface pores. Yeah, correct. Good point. Little bit about handling. These are again, I won't go through all of this stuff, but you should take the normal precautions that one takes in handling powders, right? Especially when you go to finer powders. Some of these powders can be airborne, and if there is a possibility, it's not so much of a problem in PBF, because most of it is done in an enclosed chamber. But when you are dealing with DED, etc., you should be careful, especially if there are possibilities of fuming, and therefore getting some sort of nanoscale material formation, right? That's something you should be very careful about. Good to wear masks, yeah, but otherwise these are very normal procedures that one adopts in dealing with powders. It's good to know that all of those precautions apply, yeah, as you can imagine. I mean, there are various steps during the AM process where You just don't want to stand there and do that kind of stuff. You have to do it in an enclosed environment, right? Where proper protective masks, do it in a well ventilated environment and stuff like that. A little bit about reuse. We spoke about that very briefly yesterday. Not so much from a safety and health point of view, but from an ecological standpoint, always good to try and be very aware of potential for reuse of these powders for various reasons, because these are all very expensive feedstock, right? So you don't want to use it once and throw. You can use it several times. And they are, depending upon application, capable of being used many, many times, right? I'm showing you here an image from some of our work where we have used Ti-6-4 almost 70 times, right? Here I'm showing you only the morphology here. You see, this is how you start, because the supplier is recommending spherical powder, no satellites. Here the sphericity is retained. You see some, I apologize for this bad micrograph, but you see some satellites coming up on these powders, but it can still be used. It of course has slightly higher oxygen content in the powder, right? But that is little bit application specific. If this was stainless steel, then I would use it several times, doesn't matter, because the applications of stainless steel are also little bit more forgiving. So you must relate potential for reuse and how many times, because the oxygen content will progressively increase. That is known, yeah. So you must relate this to your application in a good way, yeah. Waste disposal, also for good housekeeping again. You cannot just take the remaining powder and throw it in the garbage. There are proper ways to dispose. You should be aware of what regulations exist around you. In Sweden, we follow this regulation from the EU, which requires both ferrous and non-ferrous materials to be segregated. There is a separate rule if the powder that you want to dispose has been in contact with oil, etc. Then it goes into a different bin, because then it is classified as a sludge, yeah. So at the moment you need not worry about it, right? I'm just saying that these are the kind of things you should be aware of depending upon what you are using, right? Can't throw it in the sink or in your garbage dump. That is important, right? Let's talk about little bit wires and then get on to something more interesting. Powder versus wire. I didn't go into much detail yesterday, but wires are often a more economical choice. We've seen that all the biggest AM structures that have come out of our work have been in case of wire DED, yeah, rather than powder, yeah. So wires can give much economical output in that sense. It also gives a higher deposition rate compared to most other methods, and one handicap, however, is with a wire you can't make parts that are as complex as one can make with a powder, right? So that's one of the handicaps. Also, we just spoke about safety. Most of these issues don't apply when you're using powders, but much safer to handle. Today, and things can change tomorrow, but today the wires that we use in DED are same as what wires we've been using for welding, right? There's not much difference. And when I say wire, I'm using it kind of generically. Today people use solid wires, hollow wires, metal core wires, flux core wires, all of these can be used just as they are being used in welding, right? Uh, Drawing or rolling are the, like we spoke about atomization, drawing and rolling are the most common methods of making these wires. They are usually cold drawn. In some cases, you need an annealing step, not always, but sometimes after cold drawing, you may need some annealing so that you restore the ductility. That's true in case like titanium, for example. Uh, People resort to warm drawing as well. And when you're talking about cold wires, there are different ways to prepare that. But the guys in AM need not worry so much about that. Yeah, it's available. You use it. Yeah, and there are many people who know how to make these wires. No problem. Uh, Again, today I emphasize that all the time. At least at the moment, the AWS and ISO codes apply for all these wires that you would want to use in AM. Yes, please.
Suppose white spool is got contaminated.
Hmm.
What's the best and economical method to reuse it?
You're saying wire spool has got contaminated.
If we store the wire for long time, it will get disturbed. So if I want to use that spool again for welding, to save money and time, what is the
I don't know. I mean, you should not let. But you raise a good point. I don't know where it is, but. Maybe I ran out of space, but that's exactly the point I wanted to make on this slide, that especially in AM, etc., storage of these spools, etc., will slowly become critical. Right now, people don't worry about it for welding, but it will change, yeah, for AM for sure. So, I don't think you can revive that spool in some way. I mean, you must use it for applications that will accept the kind of damage that has happened. I think that is the best thing that I can tell. But otherwise, you can't do so much. And even if you are able to do something, it will be much more expensive than buying a new spool. I guarantee you that, right? So, it's not a good or simple way to take care of it, right? So, as I said, at the moment we are using wires that people use for welding, right? As you know, in welding and cladding, dilution is a big issue. Yeah, so people correct for that kind of stuff. They compensate for it for this kind of dilution in the wire composition. Need that in case of AM, because when you're building large structures, the dilution is limited to the first few layers. After that, there is no dilution, right? So, you may not need the kind of correction that you incorporate in these wires in case of welding and cladding. So, that's important. The other thing to remember is sometimes there is a probability of accumulating elements like oxygen and nitrogen, yeah, with increasing number of passes, right? So, this will be even more critical in case of AM, because when you build higher parts, I mean larger parts, you can get more and more accumulation of oxygen and nitrogen. So, I think even purity when it comes to high performance materials like titanium alloys, that's also something you will need to pay attention to, right? But at the moment, standards, regulations, even suppliers of traditional welding and cladding wires are being looked at by the AM community as well, yeah. And there is, of course, a very large portfolio of such wires that is available, right? Just a summary of what I said. Powders produced for welding also used in AM, and this is a caution, but that may change tomorrow. As AM technology evolves, you will perhaps have some specific modifications that become necessary in few alloy systems like titanium nickel based super alloys. And exactly the point that you made, I was looking for it on the earlier slide, but storage of AM wires will require extra caution, and that's exactly what I meant, right? When you look at much larger structures, I think any impurity uptake or even things like oxygen and nitrogen, which we tend to not attach much importance to, could become very critical in case of AM builds, right? So nobody talks about it today, but I think this could become important at some point. Yeah. I want to stop here on this one, move on to post treatment, but is it time for a break or I can start? Do you have any questions so far before? Any questions on what we spoke about this morning? Very boring subject, right? But I also agree, not much fun. Yeah, I mean, by way of a practitioner, from a practitioner standpoint, if you work with AM, you should know this, but it's not a subject of research or any such thing. But I hope you will have more fun with this one. Should I start and we take a break whenever tea is here, or should we? Yeah. So yeah. Yeah, exactly. So let me know whenever you want to take a break. Doesn't matter, but I'll begin. Yeah. So this module is on post treatment of AM built parts. I really like that. I had a PhD student who is now in Finland, Sneha. She did some outstanding work on at least thermal post treatment. She was also another student of mine who is now working on surface post treatment, and my colleague Magnus. So I've taken some of their slides. So if you look at the number of steps in AM, we spoke about this earlier, modeling, STL files, slicing, etc., printing. So we have kind of covered up to here, and on the back side here, feedstock, etc. Now post processing. We will talk about why post processing is crucial for almost all applications, right? And these are almost mandatory now before we go on to a finished part that is ready for application, right? This is another way of showing the same, right? After processing, you need to do, I'm not, as I said yesterday, I will not deal with grid blasting and removing the surface plate as post processing. That's part of processing only for me. Yeah, the real post processing really is surface, changing the surface attributes and doing thermal, right? And we'll talk about why we need to do that, right? There is, at the end of this loop, there is certification as well, as I mentioned briefly in the morning, and that's something we will cover on Friday. Deepa will come and talk about certification a little bit, right? So those are important things. Why post process? Yeah, because a produced part, people can talk about near net shape, this, that, but it is never completely ready to use, right? You need to do several things, and we'll talk about why. Yeah, and this is what you do is both process dependent and application dependent, and depending on that, you may need to use several additional steps before you can put the part in actual service, right? If you look at literature, people will talk about all of these things. Removal of excess powder, removal of support structures. For me, it's not post-processing, yeah? It's the end steps in a process, right? And then these two is what we will focus on. Finishing to obtain the desired surface attributes or geometrical tolerances, one. And second is treatments to improve mechanical properties, yeah? These two are very crucial, depending upon which material you are using to build and where it will be used, right? In many cases, just an as finished surface may be okay, right? No problem. As built, I meant. As built surface may be okay to use. Sometimes it may need mirror finish almost, right? So it depends upon where you use that, right? We spoke about this yesterday. Let me get it out of the way because these are not really close to my heart. You remove excess powder, you saw a video on that, and then this is more necessary in powder bed fusion. In DED, you don't need that. Yeah, you just need some normal machine cleanup. If some powder that you have delivered has not melted and deposited, you just get rid of that. Just a simple high pressure air blast will do. You don't need to do anything more than that, because in case of DED, the part is not covered in all sorts of stuff. Yeah, it's already there. So it's not encased in unused feedstock, right? Same with supports, right? This is a pain, but it's a necessity. It doesn't come off as easily as removing the powder. Most times you have to mechanically cut it off, right? So by applying force or by, we oftentimes use EDM wire cut to take it off, right? Yeah, over. The boring part is over. Now let's talk about surface post-processing and thermal treatment. Yeah, these are important tracks. On the last day, I'm going to give you a list for list of resources for additional reading. While I was compiling that last night, I thought I will put that here. This is a good resource for surface post-processing. Very nice review paper in additive manufacturing. But let's talk a little bit about surface integrity of AM built parts. We didn't talk so much, but a typically built AM surface is rough. Yeah, the context may vary. How rough? That may change, but it's always rough. EBM is very rough. SLM is rough. DED locally is not rough, but on a macro scale, it is undulating a little bit. Yeah, so all of these things are a fact of life in AM. And some people consider this as a disadvantage, but that's how it is. It happens because of the fact that all of these are layer by layer deposition processes. You just can't avoid not having a great surface. Yeah? It typically creates a ridge effect on both vertical and horizontal surfaces. I showed you one slide in VAM, for example, a single wall build, and you saw that the vertical wall had fairly lousy surface in that sense, right? So can't really help that. The ways to improve that, in regardless of what method you use, is to reduce the step size, right? You build it in smaller steps. We spoke about layer thickness between 50 to 90 microns or whatever. If you reduce the layer thickness, you get slightly better finish, but you are paying a price already. What's the price you are paying if you reduce layer thickness? What's the cost of reducing layer thickness? Who said that? Yeah, correct. You are directly increasing production time as you reduce layer thickness, right? So that's cost as well, right? So although you know that reducing layer thickness can yield better surface finish, it's two things. One, it is still not ready to be used, yeah, for many applications. You still need something. And second, it compromises productivity. So not a relief reducing layer thickness, yeah. But you may want to then address that surface roughness for a variety of reasons. Sometimes it could be simply because of assembly, it could be a mating part and you want a good finish. Sometimes it could be because of good looks, sometimes because of surface functionality, right? If it is rougher, maybe it is more prone to corrosion or things like that, or it gives you very bad wear in the mating part, could be anything, right? So you need to account for all of those things, right? What are the factors that affect surface roughness in a part? We very briefly just mentioned layer thickness, but there are many other things, right? The feedstock influences surface roughness. Do you all agree with that? Yeah, coarse powder, fine powder, it will affect surface roughness. How you design the part, and there is design freedom available, remember, but how you design the part, whether there are inclined features, whether during building, how are you orienting the part? Yeah, is it oriented in the build direction? Is it transverse, right? And which surface then has a greater roughness, right? So, so if you build a part, for example, I showed you the standard bread and butter build where you build the blocks. The roughness on the side is different from the roughness on the top, right? So for that reason, the part orientation also becomes important, right? Of course, process parameters, does it melt fully, does it melt too much, does it not melt fully, all of them also govern the surface roughness. We spoke about layer height already, but yeah, even the spacing between, if you're doing laser or E-beam, the hatch distance also influences that. So there are too many things that influence surface attributes, but the fact is, whatever you do, the as-built surface is not ready to be used, right? You can do your best with all of these things, but it still requires some finishing. In addition to that, there are other things that we spoke about, spattering, for example, right? If you get splashing or spattering during building or stuff like that, that makes matters even worse, right? How do you surface treat? There are many ways to do that. If you look at how they are classified, generally people talk about techniques that involve material removal, and there are techniques that kind of improve the surface attributes without removing material, correct? Although it is in this chart, I am not talking about this yet, because people look at this as surface treatment as well, or surface post-processing, but I want to deal with that separately, right? Because this is not merely to change surface attributes, but to get new function on the surface. So let's deal with that tomorrow when we talk about coatings, right? But material removal then there are mechanical ways to remove material, there are chemical ways to remove material and smoothen the surface. There are also some laser based treatments. Yeah. Uh, Kind of very busy slide, right? Mechanical treatment, easiest if your final part demands it is machining, right? Uh, People do little bit of machining. That's pretty normal. It could be grinding or milling, but if you need to machine it eventually, no problem. Uh, you may want to not really machine, but just do polishing, right? To get rid of the surface asperities. So if you do that, there are various ways to polish, including ultrasonic and stuff like that. Uh, we have we have also published a paper on burnishing. How do you burnish? Yeah, and reduce roughness. So that's possible as well. Yeah. Uh, there are some groups that explore laser-based material removal, which could be either laser micro machining or there are very fancy lasers that are available to do that. Yeah, but I recommend that you explore this only if it's absolutely necessary. It's just for me this is a research track. Yeah, these are real tracks. Yeah, for application. I don't see this as a real application relevant track. It's just to do research. What happens if I do laser texturing? Yeah, nice fun to explore, but I don't think it's relevant for a real application. Yeah, there are other methods also that you should be aware of where you can dramatically change the surface attributes, but you don't remove material. Yeah, what could those be? It could be just bead blasting. Yeah, where you can use almost like shot peening or grid blasting with softer beads where you don't remove material, but yeah, shot peening, as I said, is also widely used. A parallel to that is other laser based treatments, laser remelting, laser polishing. Yeah, all of these can also be used to change the surface attributes, right? We will talk about some of those, right? And then we go on to thermal treatment. So, talking to some of our industrial partners and making a list of things that they do, I will leave that here while we have tea. You can think about that a little bit. Yeah. Thank you. Thank you.
Yeah, we'll take.
Can we start? Yeah? Okay. So, just before the break, I was talking about this slide. So, from that very complicated table on the previous slide, this one, I have tried to extract some of the surface post-treatment tools, which according to my collaborating industrial partners, they use, right? So, I don't have a particular favorite among these, but you must know that all of these things are available for you if you want to post-treat an AM build part to change the surface attributes, right? Machining, blasting, short peening, and we have investigated some of these. We have also done some work on burnishing, as I was saying, yeah. And what is new? This is what was being done for a long time, but what is new is something that involves chemical and electrochemical polishing. This is a big thing now. There are new startups coming up in the US and in other parts, and as a part of one of the projects that we have in Sweden, there is a technique called hertization. That's from a company in the US, and this institute called RISE in Sweden has been looking at hertization. So I spoke to Swati and took some slides from her, right? Let's talk about what it is, right? I mean, we have already discussed this. The motivation for post-processing, whether it's surface roughness, taking care of internal defects, residual stress. I will come to these later, but what we are targeting right now is surface roughness, going from a part that looks like that to a part that looks like that, right? I mean, that's what we are trying to accomplish, right? So there are many material removal techniques, as I showed you earlier, and all of them are good, right? Here are some examples, again from the lab now, right? From the lab, what happens to the surface roughness if you do grinding, right? This is an as-built part, and depending upon how you grind, you can eventually get there, right? Grinding is simple, not so complicated, of course, depending upon what the part is made of, right? There are people now trying to also do by AM tungsten carbide. If you're doing tungsten carbide, then even grinding is very difficult because it's such a hard material, right? Milling, of course, you can get excellent surfaces if you choose to mill, no problem. There are some magnetic abrasive polishing techniques. So people are looking, the reason I am showing you this scientific looking slide is to emphasize that many research groups are now diving in because they acknowledge that this is a big problem. Industry is going to need solutions to surface treat the build parts. So there are many groups looking at different approaches to address the surface attributes. I spoke a little bit about laser. There are guys who do so-called laser finishing or texturing to try and remove, reduce this kind of roughness. There is some tribo finishing as well. Sorry for the typo here, but there is, this is also done by several groups. I want to talk a little bit about chemical etching and electrochemical polishing, yeah, because these are becoming more and more attractive for at least the gas turbine guys, yeah, and what we do by hertization is essentially a variant of chemical polishing or electrochemical polishing. This is another example. Just roll it with abrasive media, get substantial improvement sequentially in roughness. You can see you get a lousy part to start with, lousy looking, but near net shape, yeah, and then you want to remove the roughness, yeah. We spoke about techniques that do not remove material, and short peening is one of the more prominent ones, works very well. So you have so-called shots. The shots can be made of anything, yeah, it could be stainless steel, it could be glass beads, depending upon what is the material you want to treat. Yeah, you can do short peening and get substantial improvement uh, uh, in the surface attributes. You also can get significant grain refinement at the surface by short peening, right? So all of these are are very widely practiced uh, in the industry, at least the short peening part. This again, a regime of significant research interest using laser to polish, yeah, and you can get uh, uh, fairly good surface finish. There's something I must say here, right? I mean, uh, we have a tendency to believe that laser is very expensive, yeah, and laser is very slow, yeah. But things have changed a lot over recent times. You can raster a laser at unbelievable speed, right? And that's one of the reasons why something like this has become very important. I have a collaborator in Poland right now and also in the Czech Republic. They do this kind of work. So we have just sent them samples to be able to laser polish, and they cover large areas in less than a minute, you know. So there are these days gantries that traverse a laser at speeds which are unbelievable, and you don't need so much power, right? You're not doing great deal of processing in that sense. So with the evolution of new lasers, this has become more practical now, yeah, and affordable as well to be commercially interesting, right? Little bit about chemical and electrochemical polishing and what is the heart of hertization here. Yeah, chemical polishing, very cost effective, relatively simple. It's just like etching. Yeah, if you are familiar with etching, it's just like that. Electrochemical can give a finish which is even better than the chemical approach. It can effectively reach areas which appear inaccessible because you are dipping it in, yeah. And of course, for anything which is good, you need to pay a price. So it's more expensive than this, but worthwhile for many parts where the the geometry is very complex and there are intricate features that cannot be left unfinished, so to speak, right? So that's a way to go. So this is one of the recent equipments that we have got. Yeah. Say that again. Very good question. Yeah, I mean, it's not so well studied, but it is almost like over etching, right? And I think that's why you are asking the question, right? If you over etch, yeah, you will not get the surface that you want. So there is a lot of optimization involved there. Although I don't have data on it, I'm convinced that if you don't do this part right, you will not get such a great surface, yeah, or maybe you will even get a worse surface than before. So you need to optimize, yeah. Yeah, correct. What is? It does refine the grains quite a bit. As it's almost similar to this, right? You see a big difference in the extent of refinement. You do see that, yeah. And again, there are everything is almost a science, right? I mean, you can call it bead blasting, but there are many variables in this, yeah. At what velocity do you blast? What compressed air pressure do you use? What is the shot size? What's the material of the shot, right? All of these make difference. So, but as you can see here, you clearly get substantial grain refinement, right? And the other thing which is not shown here is some of the residual stresses that we are talking about, even those are alleviated during this process. So, yeah, quite a few benefits actually. But let's come to this. So, this is a new equipment for hertization that has been set up by one of the institutes which is not next door to us, but pretty close. Yeah, and it uses a pulsed current to control this electrochemical process of surface polishing. Yeah, and just imagine this costs almost close to several $100,000, and people are investing in this just, I mean, it's easy to say just to surface finish a built component, right? But that also tells you both things. The fact that someone will develop an equipment like this and the fact that someone will buy an equipment like this, yeah, both of these tell you that this is a very crucial step in making an AM built part worthy of final use, right? We were talking about intricate geometry. Let's say cooling hole for example. If that is not properly finished, then it disturbs the dynamics of gas flow inside those holes. I mean, there are lots of implications, right? And that's why people don't mind investing in something as expensive and as complicated looking as this. I mean, once you optimize it, is of course not so complicated, but until then, right? Very quickly, this hertization process then embraces both chemical and electrochemical routes for surface modification. I have seen this system. It lends itself completely to full automation, but there is a long optimization protocol. For every chemistry, you need to do everything different, right from the bath composition to the time for which you do it. Everything is different, but it's very interesting, and it of course is suitable for all printing methods. I don't know why they advertise it like this, because it's obvious. It is material specific, not process specific, but all these marketing guys write all sorts of stuff. But yeah, so if you have, for example, Inconel 718, there will be a certain protocol. If you have stainless steel, it will be something else. If it is a nickel based superalloy, which is slightly different, like Hinge 282 instead of Inconel, it will still be different, right? There are several challenges to overcome, including removal of support structure. This can do that as well. Treating internal channels like cooling holes. There are instances where, especially in these intricate geometries, there is loose powder on the inside, which has not gotten off fully when you grid blast, right? So it takes care of that as well, right? So, so in a sense, it encompasses what all these things try to do. At least that's the claim. I don't have, I'm not rich enough to get that equipment, but they claim this can do everything that tumbling does, laser polishing does, electro polishing, blasting. All of it can be done by this machine, kind of, right? So several steps going through this. One is support removal and just initial cleaning. Imagine yourself going through a very sophisticated electroplating setup. I don't know how many of you have seen a electroplating setup, right? It goes through various stages of cleaning, or even PVD, right? So it's something like that. First step, initial cleaning, which is quite intricate actually, but it ensures that the surface is absolutely clean. The next step is what leads to a reduction in surface roughness because of chemical and electrochemical etching. And then if you want to go beyond that, this step is optional, but then you can get a very fine polishing on the surface. as you can imagine, this is a very slow process. Yeah. On the flip side, you can load multiple parts in the bath at the same time, but it's a slow process because you are removing the roughness by etching. So it takes a while, but you can eventually get almost a mirror finish. I've seen this happen. So something new to keep your eyes open for. Yeah. So what do you consider when you do hertization? Well, biggest challenge. Even if I send a small coupon to do this, Swati will tell me, make sure there is a hole in your part, right? Because it needs to be hung. Yeah, you need to find a good way of hanging that, right? And there are other issues, not challenges in the sense, but yeah, you need to take all of these into account, and then also be very sure about what do you eventually need, right? You don't want to run this equipment for a long time if that level of surface finish is not necessary, right? So you should be clear about what your requirement is. But very exciting process to achieve what you want, right? As printed part, pretty rough. Step 1, which is essentially cleaning, and then step 2 looks pretty good, and then you can almost make it very nice. Some example that from what Swati is doing at the moment on an aluminum alloy with hertization, and then yeah, she's going through this process of optimizing this hertization protocol for polishing this, and yeah, so this is the starting morphology of the aluminum built alloy, and then you get much refined surface, yeah, right? This is the same magnification on the left, yeah, much smoother surface, so it's very good. And then if you take it even further, this is all by chemical etching. You have just dipped the bath and turning some knobs, and very good, very impressive to do that. Yeah. Before I move on to thermal post treatment, any questions? Yes, please. It's available with an institute like ARCI here. There is an institute called RICE, and they can afford it because they have some 150 companies as contributing partners in that institute, and several of them are interested in AM. So what the institute sets up is decided by a board which has these industry guys as partners. So they've been asked to look at hertization, but yeah, I know them, so I get some stuff done. But otherwise, this is something very nice. Yes. Which material? But I mean, they've been working on all sorts of things. I know. Yeah. I don't remember, but on this, if you need more data, just write to me, or if you have questions, I can get them from the people who are already using it. So yeah. So this is a more involved aspect than surface treatment. Thermal post processing, yeah, is you don't need it for all AM build parts, right? But for some AM build parts, especially super alloys, etc., this is inevitable, right? And what you need is eventually governed by what the end application is, right? So what I'm going to try and do is talk a little bit about why do you need thermal post treatment, under what circumstances, yeah? What are the different types of post treatment, thermal post treatment. I won't go too much into parameters for post treatment, but I'll give you some flavor, especially when it comes to temperature. Yeah, what happens if you post treat at a very high temperature, right? When does grain coarsening begin to happen? You don't want that. And then assess impact of these post treatments, especially on mechanical properties, because more often than not, that is what is the driver for thermal post treatment. Functional performance, not surface attributes, right? So, we will talk about that. So, motivation for thermal post treatment, I can give many reasons. One is defects. Doesn't matter how much you optimize your AM process, there are defects which are going to be inevitable, right? Some applications can live with those defects, some applications cannot live with those defects, right? But defects, what can be those defects? That could be porosity. The source of this porosity can be anything. It could be shrinkage porosity, it could be lack of fusion, it could be something that we discussed in the morning, originating from your feedstock, yeah, because so all of these, depending on application, something like this can be a reason for doing post treatment. Sometimes it could be non-uniformity, right? If we build a part like this, for example, we find that the face constitution is little bit different, yeah, at different location, because all of them have seen, each location has seen a different thermal history, right? Why has each location seen a different thermal history? I must explain a little bit more. Imagine that this part is built by EBM, yeah. Why has this location seen different thermal history, all of them? Why should there be a change in phases? Anyone? Yeah? Correct. Your first answer is correct. Now you should not make life difficult for yourself. Your first answer was perfect. Now you are talking about heat affected zone and diffusion zone. Now I will ask you to explain. Please explain. Yeah. So far you are correct, right? So for example, imagine that you start building, yeah? It's EBM, your bed temperature is 1000 degrees, right? And this is taking you 6-7 hours to build, right? So this part has seen 1000 degrees for 6 or 7 hours, yeah? This has seen it for 4 hours, 3 hours, 2 hours, yeah? Enough. That is enough to cause a phase change, right? Let's not talk about heat affected zone and make it too complicated, right? Because for that reason the temperature history is different, and therefore the phase constitution in each layer can be non-uniform, right? And you may therefore require a thermal post treatment to nullify this non-uniformity. What else, right? You may want certain strengthening phases in your build structure. Many of the superalloys are precipitation strengthened superalloys, right? And therefore you may want to ensure that this kind of precipitation happens in the part before you build it, right? So that could be one of the reasons. How many of you have heard of Lave's phases? Anyone? Anyone has worked with superalloys? Yeah? But in any case, then believe me that these kind of Lave's phases form in many nickel based superalloys, and these are usually detrimental from a mechanical property standpoint, and you want to get rid of that, right? So that could be one of the reasons for post treatment. We spoke little bit about anisotropy, yeah, in the build direction and in the direction transverse to that. So this kind of post treatment also meant to address issues of anisotropy. And finally, residual stress. More in case of EBM, slightly less in case of SLM, but there are parts when residual stresses are of course high and undesirable. So you may want to post-treat to alleviate those stresses, right? So let's look at what kind of thermal post-treatments can you carry out. One is you can do it at low pressure, or you can do it at ambient pressure, or you can do it at high pressure. Generally, low pressure treatments can be done in a controlled atmosphere, as indeed these ambient pressure also. If it's low pressure, it's vacuum. If it's ambient pressure, you can use argon or something like that, yeah, to do the heat treatment or thermal post treatment. And you can do it at high pressure, which is like hot isostatic pressing, yeah. We will come to that in a little bit. But do remember that these thermal post treatments are integral to improving the mechanical performance of the part, and therefore for most high performance applications it's unavoidable, correct? And therefore you must have a good idea of how the mechanical properties are improved, and in the process you should be able to control the microstructure, because that is what will govern the mechanical properties, right? So in that sense very complex compared to surface post treatment. Thermal post treatment is very complicated, takes a long time for it to be investigated, and therefore even longer time later for it to be qualified by the user and put in practice, right? So two prominent approaches, one involves hot isostatic pressing, the other involves in one sense traditional heat treatment. Let's talk about hot isostatic pressing. It involves, as the name suggests, it involves pressing at high temperature, yeah, and also at high pressure. The typical gas pressure can be varied over a fairly wide range. Usually you see equipment that goes from 35 to 200 megapascal, and you can of course vary the temperature also over a fairly wide window, of course always below melting for sure, but as a thumb rule it's good practice to do this at about 0.7 times the melting temperature, yeah. So we've done this heat treatment over almost this entire pressure range. We have done it at different temperatures as well. We have a good partner in a company called Quintus. I don't know how many of you have heard of Quintus, but it's one of the leading manufacturers of HIP equipment today, right? And then we've been fortunate to be able to do all our hipping in their systems in Sweden. Let me see if you can hear what is being said, but
the more complex the technology, the more important to focus on the details. We must minimize the risk of inconsistencies in our materials in order to be able to take product quality for granted. Materials formed from casting or additive methods.
I'm showing it for two reasons. One is because it's a very important step in thermal post treatment, and second, I want to be nice to them because they have been very nice to me in running all my experiments. So
methods such as 3D printing contain porosities or microcavities. These porosities must be reduced to eliminate the risk of premature breakage. This is usually done in two steps. Firstly, heat is applied under pressure in a HIP process which reduces porosities and cavities. Secondly, the material is heat treated in a process where rapid cooling improves the fatigue and ductile properties. It would be a big advantage if these processes could be combined to save energy and increase productivity. But combining quick cooling with high pressure places stringent demands on the pressurized furnace. The vessel needs to be robust enough to withstand the high pressure while also being cooled quickly from the outside. By adding a wire package to the outside of the vessel, both can be achieved. The wire package allows the inner wall to be thinner for quicker cooling, with maintained structural integrity of the pressure vessel. The thinner wall enables a unique heat exchange system, which makes it possible to cool down the load quickly and meet the requirements of the heat treatment process. This means that the HIP process and the heat treatment can be run at the same time in the same vessel, saving time and energy. Through the Quintis Uniform Rapid Cooling System, URC, the hot gas is pushed towards the thin-walled vessel. At the same time, the vessel wall is cooled by water from the outside, while it is supported by the wire package to keep it safe and under control throughout the process. With this unique combination of HIP and heat treatment in one, the load only needs to be heated and cooled once. This gives significant savings in productivity and energy costs. In addition, continuous cooling under pressure reduces tension and the risk of future material breakage. Combining the two processes also saves space, reduces the need for process infrastructure, and cuts equipment investment costs. When looking at HIP and heat treatment to improve material properties, safety, capacity, and energy cost are important factors regarding both the investment and the operation. Combining the processes offers many benefits and enables more components and details to be treated in a way that ensures they will perform the way we expect. Quintis, the global leader in high-pressure technology.
So I hope that gave you some insight into what hipping is all about and what it can do. But oops. Having seen how it works, I must say that there are three key parameters: temperature, time, pressure. And all of them mean money, especially time, right? So you're always trying to reduce the time for pre-treatment. And since we have worked so closely with these guys, they use many of our results for their marketing now to the AM community. So yeah. So typical goals. HIP is not new. HIP has not been developed for AM. That you must understand. HIP technology is fairly old, and the typical goals for using HIP have been to, of course, always get better mechanical properties, produce the final product by the powder metallurgy route, right? I mean, there are enough hipping equipments actually in India itself, yeah. But so we are now using this existing technology, which has been especially in vogue for powder metallurgy components, and now you want to use it for additively manufactured parts to both enhance properties and eliminate defects, right? The driver for that is essentially to remove defects. That's what hipping really does. Yeah, remove pore defects and therefore lead to augmentation of all sorts of mechanical properties, whether it is yield and tensile strength, ductility, much improved, fatigue life. This is what our results have shown so far, and also equally important is the fact that it reduces or eliminates rejects, because of defects and things like that. Yeah. I don't. Something I want to emphasize here, what we mentioned yesterday, that the open pores cannot be healed by hipping, only closed pores can be healed. Yeah, and I will leave it at that now. Maybe when there is, maybe I talk about it now. Yeah, why are open pores not healed? Anyone? What's the problem with open to surface pores or defects? Why does hipping not deal with those in a good way?
There's a risk of breakage.
Risk of breakage.
Pores can reduce the strength of the material.
Open to surface. Yeah. So it could just be something like a cavity on top. It could be interconnected porosity which goes inside, but is eventually open to the surface. Those kind of pore hipping cannot close. Yeah, those kind of defects. Why do you think that is the case? No, it's simply because then if it's open, then the application of pressure has no impact on the microstructure because it's open, right? So on the other hand, if it is closed, then application of pressure and temperature can heal that defect. Correct, right? So one of the things we have been trying to do, I don't think I have any slides on that. One of the things we have been trying to do is see if we can coat the part and then hip. Yeah. So if there is an open to surface porosity, then it becomes closed porosity because of the coating. The other alternative, of course, is encapsulation. I didn't talk so much about that, but in hip many times you encapsulate the part and then hip, right? But that is impractical for many large aero engine parts. You cannot encapsulate the part. But many of these parts could require coatings eventually for surface protection or whatever reason. So one of the projects we are dealing with is, can we coat first and then hip, so that the coating itself will serve as an encapsulation and therefore not have open to surface porosities. Unless they are present in the coating, then that doesn't help, right? So that's one of the things we have been looking at. So influence of heat treatment on porosity. What I am trying to show is couple of things. Yeah, one is conventional heat treatment at 1120 and 1185 degrees. This is as built. So if you do conventional heat treatment, it does nothing to the porosity, right? But if we do hipping, it reduces the porosity quite a bit. Why 1120 and 1185, you may ask? These are crazy temperatures. I was talking yesterday about standards, right? There are standards for wrought and cast 718, yeah, that talk about heat treatment in the temperature range 1120 to 1185. So we decided that we would heat treat at the two limits of that range, because the standard says 1120 to 1185, right? But the message here is no densification happens in conventional heat treatment. All the densification happens only in a hip, right? This is another example of how hipping can very nicely get rid of defects, right? As it is, if you do your AM well, there is not so much porosity, right? I mean, this is an expanded scale. We are only talking about 0.7 volume percent defects. That's not much, but that's not much depends upon what's the application. If you're talking about aerospace, they will say that's a lot, right? We can't deal with that, yeah, especially for some rotating parts, etc. We don't want 0.7%. In that case, this becomes unavoidable, then we do hip, right? But the take home message is that hip extremely effective to get rid of any kinds of pores and defects, right? Let's take that little bit further, right? I mean, as I told you, these are the two limits of the temperature over which which is specified in the standard for traditional 718. So we've done this hipping at two different temperatures, 1120 and 1185, and you can see here, yeah, slightly better properties for 1120 actually, right? But in both cases you get almost full densification. I don't know if I have, maybe I don't have. I don't have data here for microstructure, but as a part of this study by Sneha, we realized that at 1185 you begin to see coarsening of the grains, right? So most of our work then we restricted to 1120 degrees hipping, right? So the next question which came to our mind is, if you're going to hip anyway, yeah, and certain applications make hip unavoidable. So if you're going to hip in any case, how does it matter how you have built it, right? Is that a good logic? Suppose the application requires me to hip, then why should I worry about optimizing my EBM parameters, for example, to get a very good build? How do I care? Because I am going to hip it later. Is that a good argument? It's a lousy argument, or? It's not a good argument. Why?
Because more we get the defects, the more weaker the material is. Even if we not hip also, even we think that it's just a minor thing, and we hip it, but depends, that structure is depend on the strength of the material. The more we get, the more weaker it is.
But you are not going to determine strength in as-built condition. You are going to eventually hip, right?
But that hipping process is the secondary. The first, the material should be clear or the stronger.
Why?
Other applications now.
No. You are doing hipping, all thermal treatment you are doing, so that you eventually get mechanical properties that are of interest to you. You don't care what your as-built thing looks like, right? That's the reason you want to post-treat.
Phases that are formed will not happen due to probably in as-built condition only the required phases are formed.
In as-built condition. Yes. But after that it is going to see all sorts of thermal treatment.
But the parent phase required may not be formed.
Which I can guarantee will not form anyway. Yeah, if you look at a nickel-based superalloy, if you look at how it is put to use, it has to be solutionized, it has to be double-edged, yeah, to get the precipitates that we spoke about, right? So all that action is going to happen later anyway, right? And that doesn't happen in as-built condition. Yeah, when you do EBM or SLM of a superalloy, you don't get a phase constitution that you want. As I showed in the motivation, in fact, you get some Laves phases and things like that, which you must get rid of, right? So, in particular, let me refine that question better. If there is a way for me to EBM build faster, right, and doesn't matter if instead of 0.7% porosity, I get 5% porosity, yeah, but it allows me to build very fast, yeah, then is it a good idea if I am going to hip? That I build fast and then I hip and do something like that. Yeah? If we don't have an answer, we also didn't have an answer. We are looking for an answer. Yeah? So, we constructed this experiment, right? So, we intentionally built in ABM, in an EBM, samples with very different porosity. Yeah? We intentionally introduce defects. There are many ways to introduce defects intentionally while you are processing. what we did in this case was only change the melting speed, right? All other process parameters same, we change the melting speed. And then what happens? We get very lousy microstructures, right? Very, very bad, because you are building it very fast, right? This is scanning speed, right? So if you go from 0.6 to 1.8, you are building it 3 times faster. Yeah, everything else is same. You are building it 3 times faster. Yeah, and if you build 3 times faster, as you expect, you get horrible microstructures. Yeah, but in this case, they are intentionally produced. We have produced those defects ourselves on purpose, right? So initial as built under normal cases 0.5 to 0.7 that I showed you earlier. If you build little bit faster, 2.7% defects. If you build it very fast, 17% defects. And then we hip it, yeah. Voila, everything gone, right? And that is what we wanted to try and show. That this is a little bit tricky, but you must understand. We could do it in this case because we are targeting applications which absolutely make hipping mandatory. Not all applications require that, right? So this is only for cases where you already know that you are going to hip, right? Because the application cannot allow you to put that part in application without hipping. And because we know that we are going to hip eventually, then you can think of a strategy like this. Yeah, but if there are applications that do not absolutely demand hipping, then this is a bad strategy, because then it forces you to hip. Yeah, that's not what you want to do, correct? Then you are better off building it like this, because that application may be okay with 0.5, 0.7, correct? So you need to be a little bit careful in what you decide. What looks like a great idea here may not be a great idea for some other application, correct? But this for us was very promising, right? So this is the question we were asking, that if you're going to hip in any case, can you build faster? And looks like the answer is yes, yeah? At least based on these studies. But this is just microstructure. So we did several things after that. We exposed this to high temperature. How many of you have heard of thermally induced porosity, right? You have heard of thermally induced porosity, right? So that can happen. It can look like a nice microstructure, but when you expose it to temperature, it can open up again, yeah, and give you porosity. But we tried it in that case and didn't happen. But when does the hip not do its job? So there were very few little dots here, you see, yeah. So we were trying to see what is going on there. So we found that the only places where hipping doesn't densify is those where there is some inclusion, right? So related to the feedstock, right? Very high magnification here. So this scale is about 9 microns or something. So we find that wherever there is some oxide inclusion, that is where it doesn't successfully hip. But otherwise, it densifies everywhere. Yeah. Influence on build properties. You should always keep an eye on microstructure. One. Yeah. Then you must look at it deeper. For example, here everything looks nice, right? Everything looks dense. Here it looks dense, here it looks dense, right? But then you go one step further, look at it one more time, right? 1120 degrees. So this is, we spoke about contour and hatch yesterday, contour and then hatch in between. So this is the microstructure in the contour, slightly different than in the hatch because we use different parameters. Yeah. This is after hipping at 1120 degrees. This is after hipping the same sample at 1185. Yeah. So you begin to see grain coarsening now. Yeah. Everything else same. Same pressure, same duration, different temperature. You see grain coarsening. And this is something you don't want. So although your pore healing is effective or defects are gone, you don't want grain coarsening, correct? So that's how we decide on using 1120 then, right? So grain growth during hipping is something that you want to avoid, right? Uh, we've looked at this aspect in great detail. We have also begun to look at how different AM processes respond to hipping. So we've looked at, for example, EBM and SLM. And we find that there is more grain coarsening in case of SLM for some reason. You also see a structure that is very different. Yeah. In one case, you have a columnar structure. In another case, at least when you start, you have an equiax structure. Correct. So it's good for you to know that these things can happen, right? And then we have intentionally, just like we intentionally tailored defects, we intentionally tailored microstructure while building high aspect ratio columnar, low aspect ratio columnar, mixed columnar with equiaxed, fully equiaxed. And we always found that if we had equiaxed, the grain coarsening was much more, yeah, in the sample. So you can play around quite a bit with this, but important to know what goes on, right? Effect of hip on these phases, delta and gamma double prime. That's also we investigated a lot, and then we found that if you hip it under the right conditions, it can dissolve the delta and gamma prime phases and lead to a much more homogeneous matrix, as you can see here. So not only are the defects gone, these kind of phases are also effectively taken care of during hipping, right? What else? We spoke about inclusions. So if you have inclusions such as alumina or titanium nitride, yeah, which come from the feedstock, yeah, hipping does nothing to them, right? So they are retained even at the end of hipping. So hipping gets rid of pores and defects, but it does nothing to the inclusions, right? So that's the message, correct? Any questions about hipping? Yeah, because when you do thermal post-treatment, hipping is the first step, right? Where you are essentially getting rid of defects and pores, yeah, and to some extent ensuring that your delta phase, etc., is gone. But even if that didn't happen, that is the purpose of carrying out the heat treatment later. So the main motivation for hipping is defect closure, right? Nothing more. So any questions about that, or can we talk about heat treatment then? So let's talk about heat treatment. Yeah. No. I'm saying that again and again. It is not it's not to be used for all applications. It's an expensive step. Yeah, it's an expensive step. So you don't, if you can avoid hipping, you don't want to hip. Yeah, and I want everyone to be clear about that. You don't want to combine two expensive processes. AM itself is expensive. You don't want to combine it with HIP. And HIP also is a very sophisticated equipment. Most companies will not have HIP. They will send their parts out to some facility where it can be hipped. Yeah. So hipping is to be avoided if your application allows you to avoid it. Correct? So we are asking ourselves the exact opposite question, right? That if you know that you have to hip because your airworthiness certification demands hipping, then what can you do, right? So everything that I showed you so far is assuming that you cannot do without hipping, and then what happens if you do it at 1120 degrees, 1185 degrees, if you do it on a good build, bad build, yeah. But for that, the answer to this question do I need to HIP? Should be clear at the beginning, right?
What is the simplest thermal heat treatment of an AM product so that we can enhance the product?
That's a don't take it personal, but that's a bad question to ask. Yeah, why? Because it depends upon what material you are building it from, yeah, and what is the application. So if you say if I have done my build in stainless steel, yeah, I may say no, why are you heat treating? I will ask you the question. If it is Inconel 718, I will tell you a certain treatment which I am going to talk about. But if you're talking about Haynes 282 or TI 64, what I talk about will not be relevant. Something else may be relevant, right? So there is nothing like an ideal heat treatment. You must understand that it is material specific. Yeah. So let's talk about that, and then if you still have that question, we'll talk about that more. Yeah. So let's talk about conventional heat treatment and its relevance to AM. So you know what heat treatment is, right? Yeah. You take the material to a certain temperature, hold it for a specific predetermined duration, and then cool it. You can change various things here. Yeah. So the real money is in knowing how to heat treat, right? It could involve various things. At what rate do you heat it up? Yeah. At what temperature do you hold and for how long? And at what rate you cool down? All of them are important depending upon material, right? And therefore it is crucial that you understand for your material system what it should look like, right? Let's start off for what is often the most basic step for heat treatment, right? And this could be true irrespective of material many times. Yeah. Imagine that you have lot of residual stresses in your part, yeah, which is usually true in case of laser beam powder bed, also true to some extent in case of DED, and then it is very common to perform a stress relieving heat treatment, yeah, at whatever condition is appropriate for that material, correct? Yeah. So they're usually at a reasonable temperature and time, but if you do that, you can see how it looks like after you heat treat. There is a substantial alleviation of stresses, and that's what you must accomplish. The same thing that I showed you for hipping still holds. Your time and temperature should be such that you avoid grain growth and recrystallization. You don't want that to happen, but you want to relieve the stresses, right? So therefore, this may require some optimization for the material that is of interest to you, right? So if you ask me from an AM perspective, what kind of heat treatments are relevant, I think this is almost commonly used stress relieving heat treatment that we quickly spoke about. I talk about that again and again. You don't want grain coarsening because that will adversely influence your mechanical properties. The other kinds of heat treatments, these two are very material specific, and I am going to today give you examples that are related to Inconel 718. Yeah. But they will be applicable to many other superalloys. Yeah, one of them is solutionizing treatment, also known as solution annealing or homogenization, right? Where the idea is to ensure that any elemental segregation that has happened during building is nullified. Yeah, you want to dissolve undesired phases like laves and delta phase that I spoke about, and kind of prepare the material for aging which follows, right? So that is the purpose of your solution treatment, and then the aging it depends upon material, but the intent is to ensure that all these strengthening precipitates appear, yeah, uh, through suitable heat treatment, so that your mechanical properties are improved. Do you want to watch a video? We have time, right? Yeah. So let's look at that, because I think this is important. Uh, it's important if it works.
Hey guys, welcome to Skilling. We are surrounded by a large number of objects, and each object has its own properties. In one of our previous videos, we saw different types of crystal structures that contribute to the properties of the materials. But there, we've covered only the structures of solids made of a single type of atom, in other words, pure substances. In reality, almost every object has impurities in it. Sometimes, impurities are also added to the substances intentionally for improving their properties. One such addition of impurities to other substances yields solid solution, and that is what we're going to discuss today. We'll be discussing what solid solutions are, why do we need to study them, and the types of solid solution and the rules governing them. Let's start with what an alloy is. An alloy is a mixture of metals formed by adding a certain amount of metals, called alloying metals, into another metal called the base metal. This is usually done for obtaining the desired properties. For example, pure silver is anti-corrosive, but it is also very soft. Adding a certain amount of copper to silver forms an alloy called sterling silver. This improves the mechanical properties without affecting its anti-corrosiveness. Alloys can be divided into two types. They are solid solutions and intermetallic compounds. A solid solution is a solid state mixture that contains two or more solutes in a solvent. A solid solution consists of a single phase throughout, and the crystal structure of the solvent remains unchanged even after adding the solute. Whereas, when the crystal structure of the alloy is different from its constituents, then it is said to be an intermetallic compound. Another major difference between these two is that the composition of the intermetallic compound is fixed, whereas the composition of the constituents in a solid solution may vary. For example, a copper and nickel solid solution may contain different combinations of copper and nickel. But why do we need to study them? As mentioned, adding a metal into another changes its property. The property of the alloy changes according to the composition. Therefore, for selecting a material for a desired application, one should know the concentration of the metals, which shows the required properties. Now, let's move on to see the different types of solid solutions. Based on the location occupied by the solute atoms, solid solutions are divided into two types. They are interstitial solid solutions and substitutional solid solutions. If the solute atoms occupy the interstitial space, that is the space between the solvent atoms, then the solution is said to be interstitial. On the other hand, if the solute atoms replace some solvent atoms and take their place, then it is said to be a substitutional solution. Substitutional solid solution can be further classified into two types, namely ordered solid solution and disordered solid solution. In an ordered solid solution, the solute atoms take a fixed position among the solvent atoms and are arranged in an orderly manner. Then it is said to be an ordered solid solution. This type is seen in aluminum-copper solid solution, where the aluminum atoms occupy the corner position and the copper atoms occupy the face-centered position. If the solute atoms occupy random positions in the crystal lattice, then we call it a disordered solid solution. Most of the solid solutions are of this type. Well, that's all about the types. But do all elements form solid solutions? The elements should possess some similar properties to form solid solutions. Hume-Rothery put forth a certain set of rules that state the conditions for metals to form solid solutions. First, both the solute and solvent atoms should have similar atomic radius. The difference between the radii of the atoms must be less than 15% so that they form a solid solution. Then, both the atoms have similar crystal structure, which favors the formation of solid solution. Next, the electronegativities, that is, the nature of the atoms to attract electrons, should be the same. And last, they should have the same valency. Well, that's all we're going to discuss in this particular video.
Actually, I wanted to show this so that I could sit down for 5 minutes. Essentially to take care of that, and then aging. Yeah, there are specific aging protocols. There are in fact standards available. Yeah, of how you age. I should have put that standard here, but no matter. If you are looking at wrought or cast Inconel 718, it calls for a solution treatment which is, I think, 1 hour and 15 minutes long. Yeah, and then it has a 2-step aging, which is 8 hours plus 8 hours. So, can you imagine, you are doing almost 20 hours of heat treatment, including heating and cooling, to eventually get what you have built in a form that is usable. 20 hours, right? So again, little bit of the same solution treatment to dissolve unwanted phases, aging to form and grow precipitates of interest. Yeah, and Inconel 718 is a precipitation strengthened superalloy, right? And that's the reason why you have the kind of aging treatments like I specified just now. Yeah. Oh, I thought I didn't put the standard, but looks like I have, right? So if you look at the standard out there, which is specified for powder bed fusion, yeah, there are all these numbers for the standards. They involve a solution treatment in this range, yeah, 927 to 1010 degrees for 1 or 2 hours, followed by either water quenching or air cooling, and then they involve a 2-step aging. 8 hours at about 720 degrees, another 8 hours at 621 degrees, total time of 18 hours. Yeah, so that's a standard for you to get what precipitates you want. So we've done various things. We have taken an as-built specimen and done all that. We have taken a HIP specimen and done all that. Yeah, and then we have also in both of these cases stopped specimens at that stage, and at that stage, correct, to see what's happening. Our real objective was to also answer the question, do we really need 18 hours, right? Maybe it's in the standard for a wrought or cast material, but in an AM material, do you need 18 hours, right? So those were some of the questions we were trying to ask, and therefore, to answer that question, we said, let's break this up. Yeah, for example, the solution treatment, 1 to 2 hours is specified, but let's see what happens after 15 minutes, half an hour. Yeah, at various intervals, even for aging. Let's look at 1, 4, and 8 and see if it makes sense for us to stop any of these treatments at some level, right? Thinking that we have already accomplished what was meant to be accomplished as per this standard, right? So that was the motivation. So just some quick results for you, right? So this is as built with delta phase decorating the grain boundary, right, in an Inconel 718, and this is without prior hipping, but we did it for 15 minutes, 30 minutes, 45, 60, right, in both of these cases. And then you see that you begin to see these kind of grain boundaries at, I mean, delta phase decoration at about 45 minutes, right? But not big difference between 45 minutes and what's in the standard. So, no great motivation to look at solution treatment further, right? Let's look at aging, right? You want to age it just right. So you want to perform what is kind of called as peak aging, right? To get the right kind of mechanical properties. You don't want to underage, you don't want to overage, because on either side of peak aging, you begin to compromise the mechanical properties, right? And that's the reason we wanted to investigate this at various instances. So, these are some of the micrographs at various stages. This is almost at the beginning, where you have a super saturated solid solution. This is showing some strengthening precipitates, but small, tiny, so reflective of underaging. This is when we do it for too long and get very coarse precipitates, right? So, we were trying to hit this particular peak aging condition, right, and that was the motivation. As you know, precipitation happens because of supersaturation, and that's a condition you need to reach, right. Once again, as a reminder, the idea was to try and shorten the post-treatment protocol, because that is what costs money there, right. So, this is a summary of everything that happens during aging from the samples that we were looking at. So, this is a hip sample, this is an as-built specimen. After hipping, you actually see a drop in hardness, because it has homogenized. Whatever other undesirable phases were there have vanished, and you get the same effect as you get during hipping, during solution treatment. But what is interesting is what happens during aging. The first step of aging, 1 hour, 4 hours, 8 hours, and then second step of aging, 1 hour, 4 hours and 8 hours, right. So, our argument then was that you've already accomplished what you needed, so not much difference there. So, can we stop this after 4 hours, right? Here you have achieved this right after 1 hour, so can you stop it after 1 hour, right? So, can you convert your aging, two-step aging, from 8 plus 8 hours to 4 plus 1 hour, right, and shrink that, because that's a substantial reduction if you can go from 18, 20 hours to 5 hours, right. So, most of what I show you now is to impress upon you that you can shorten these heat treatments, right. So, this is evolution during aging, 1, 4, 8 during stage 1, and then 8 plus 1 and 8 plus 4, right, during, so we've looked at all that, and then we think 4 plus 1 looks pretty good in terms of precipitation compared to the current standard, which is 8 plus 8, right. So, so that is one way in which, for any given material that you are interested in, take a look at whether the existing recommended thermal post treatments are appropriate, or is there room to make big changes in what is presented as a standard at the present time. Yeah. So, we are at the moment we are in a state of flux, because it's still new, AM. So, people are borrowing standards which have existed for a long time. Yeah. So, same standard for cast and wrought 718 continues to be passed off as standard for AM built 718, and that's perhaps true for all other super alloys and things like that as well. So, so just a quick summary on what is accomplished by these thermal post treatments very quickly. Defects, we saw that HIP will eliminate defects, but simple heat treatment will have no effect, nothing will happen. If you are looking at inclusions, neither heat treatment nor HIPping makes any changes to the inclusions. Same with the carbides. Hardness directly correlated to the strengthening phase, the gamma double prime, right? It depends upon how your gamma double prime evolves. Yeah. Speaking of which, the gamma double prime, you see that it completely dissolves during HIPping and also during solution treatment. That's why you see a drop in hardness, if you remember. Yeah, and then it precipitates, of course, during aging, right? So the heat treatments have an influence on all of these, right? Including not the least the grain size. We saw that even between 1120 and 1185, there is a big difference in grain size, right? So, and you don't want that kind of coarsening to happen, right? So the takeaway message for me is that the standards which currently were existing for standard wrought or cast materials may not be ideal for AM. They will work for AM, but I think you don't need to spend so much money to do a 20-hour cycle when you can do it in 5 hours, right? I've only showed you microstructures and things like that, but where is the proof? Yeah, because eventually you want to see mechanical properties. So we have tried to do this at different levels. We have looked at ductility and tried to compare. I mean, this is irrelevant what as built looks like, but you really want to compare how does the 4+1 cycle compare with the 8+8 cycle, right? So we've done it for ductility, looks pretty good. We've done it for the ultimate tensile strength, looks nice, not very different. So it seems like everything plateaus kind of at 4+1, right? This is another way of presenting the same thing from different builds. So we wanted to be sure that the way you build is not influencing our data. So these are same material built at different times in different equipment, and we are then trying to compare how this looks like, right? So looks quite nice. We've been using this kind of an equipment for HIPping. The reason I showed you that video from Quintus is now this equipment allows us to do not just HIPping, but HIPping plus solutionizing plus aging in the same furnace, right? So our next ambition was that can we do this 4+1 cycle inside HIP, because we are HIPping it in any case, right? So we that is what we began to explore, because this facility provides us that possibility during the because of the ultra rapid cooling or quenching that is possible in their furnaces. So we thought, let's try and program this in the following manner, right? Combine the HIP plus heat and solution heat treatment, age it here, and do it all in a single program, because most companies like to see that. Certainly the two gas turbine manufacturers who are our partners, because it leads to direct saving in lead time, cost, because you need to ship it out for HIPping in any case. So do everything there, right, inside the HIP. So this then is our constructed cycle. This is the standard solutionizing for an hour 8+8, and then this is what we decided to do inside the furnace, right? So HIP it, cool it, take it to solution treatment, do 4+1, and what goes in comes off here. So this is a truncated thermal treatment cycle in one sense, right? And super good actually. This is with the shortened heat treatment done inside the hip, yeah, by combining that. So I think this is a great result for us. Now we are also getting a little bit greedy, trying to see, do we even need solution treatment if you are going to hip at 11-20 degrees for an hour? Can we skip solution treatment also? So that is our data at the moment. If you eliminate solution treatment, so we don't really know whether this is acceptable to the users or not. But this is for a specific material system, but I would like you to kind of think along those lines, right? If you're looking at a new material but done by AM, maybe all the post treatments that you would otherwise do would be completely different, right? I don't want to show more data, it can get boring, but we've done all sorts of testing on it, and then in each case we show that the existing standards are not relevant, right? So for this module, I hope I've been able to show you that post processing is crucial in case of AM, whether it is surface post treatment or thermal post treatment to get the mechanical properties that you desire. These post processing steps are material specific in case of thermal treatment. They could also be process specific in case of the surface post treatments that you do, right? But this for me is the most important, that the existing standards don't necessarily apply. Existing standards for traditionally produced materials don't necessarily apply to AM. Yeah. So I'm happy to stop here, but I can take whatever questions you have. Yeah. And I was happy that yesterday evening someone actually called me and said, "Sir, can we meet for some time?" Right. So if you guys want to meet me, send me an email, and it will be nice. I'm staying on campus anyway. Right? Thanks for your patience. Putting up with me for 3 hours or 4 is not easy. Yeah? But any questions now or later? Tired, hungry. Yeah.
Definitely, post-heat treatment will provide refinement of grain structure.
Oh, please be careful.
In aspect of nursery material.
But ask your question.
Yeah.
Let me answer.
Suppose if I go for heat treatment of a temperature below the solidus temperature, can I get refined structure? For additive method.
First of all, do you need heat treatment?
Yes, sir.
Yeah.
To refine structure. I mean, I would like to go for heat treatment so that I will get refined grain.
But you rarely do heat treatment to refine a structure, right? If you're doing heat treatment for accomplishing other things, let's say you want stress relief, yeah, or you want solutionizing, or stuff like that, then you want to ensure that you use a protocol that is appropriate for that, but ensure that there is no grain coarsening. Yeah, as we saw from some data at 1120 and 1185. Everything stays the same at 1120. 1185 suddenly you begin to see coarsening. So that's the operating window that you want to avoid. But I don't think you would do treatment to refine a material, especially in AM. I've not seen many users even wanting to do that. We could talk more. because I think you are unhappy with my answer and I'm unclear about your question, so but we could take it further.
Yes, one more question related to HIP we explained. I had a method called ECAP.
Yeah?
What is, can you comment in additive manufacturing case regarding ECAP? Advisable, not advisable?
As I said before, I would always avoid any post-treatment if I had the luxury to avoid it. Yeah, if I can avoid not doing any surface post-treatment, thermal post-treatment, that's great, that's perfect, right? But depending on the application, I may not be able to avoid, right? So we spoke about different forms of surface post-treatment. Yeah. For thermal post-treatment, I would do a stress relief, or I would do heating. Yeah. To the extent that I know, the only guys who demand heating are the gas turbine guys at the moment. Nobody else requires heating. Yeah. And we should keep it simple, as long as the end user doesn't demand these kind of post-treatments, you must not get it. So for example, AM plus ECAP. I don't even know what is the merit of doing it. Yeah. Yeah, correct. So I don't know. Yeah. Correct.
Severe process.
Yeah. So why would you want to do that? I didn't. That's why I said I didn't understand your question, but you could talk more. I also, although I have worked so many years in coatings, I always say that if you can avoid coatings, avoid coatings. I mean, only if you have no choice, then you should look at all these things. Anyone? Yeah?
Sir, actually, PN material is very cheap, so to do additive manufacturing. PN as a feedstock is very cheaper to do
PL.
polymer.
Yeah, okay.
But sir, metal, since it is very costly from commercial application and research application, so which kind of metal powder we should use so that research is cheaper?
Oh my God. Which kind of powder you should use so that the research is cheaper? That's a tough one. No, that's not how you should ask the question. But let's talk separately about that. Yeah. Research always happens once you have a problem identified that you want to solve. So what's the problem? Yeah. Well, I think once you're clear about the problem you're trying to solve, all these questions get answered. Yeah. What material? What process? Now all this will depend upon what problem are you talking about. Yeah. So at no time should you begin by asking what is the cheapest way to start research. No, it's not the right beginning. Yeah.
Sir, in electrochemical etching,
Yeah.
how you remove the support material without affecting the base matter?
That's challenging. Very, very challenging. So,
After support the removal will go for that.
yeah. So
The sir mentioned that we can remove support sections also using that.
they do that.
Are very thin,
Yeah.
simple.
But still, his question is very relevant because it's a dipping process. So I'm not sure if they do some sort of masking, if that is possible. But it's a good question. Let me check and see if I can get you an answer. It's still new. Hertization is extremely new and we can evolve it. So, and I think at every stage these kind of questions crop up. So I'm sure at the moment they think they can be done, but they have only been working on coupons, right, of the kind that I sent. So, but good question. Let me see if I can check and get you an answer.
Neither choice.
No?
So we'll end the session here and we'll come back at 2:30. And as well, how sustainably we can make use of this models for additive manufacturing aspect. And I'll give you some general data regarding, because as we talk the so much of the powder production with respect to additive when you comparing with the subtractive manufacturing process, we need to know how much the greenhouse gas effect is going to cause for environmental effects, what is the cumulative energy and demand is required, how much electricity we are using for our additive manufacturing machines productions, and additional and as well as for the gas and as well as for the powder productions and all. See, you are all aware that just the general data, one of the review article has given this cumulative energy data, because this cumulative energy data is required when we are thinking to manufacture the machines of additive machines or the powders or as well as the gas productions, right. This cumulative energy data requires like lot of environmental effect. What are those environmental effects? One is with respect to the production of machines, because even though we produce the machines whether conventional or additives, there is an environmental effect. And other one is how we are making this, the usage of the machine, the generation of the electricity, because to run the machines we need to have the electricity. And apart from this, the production of the machines, production of the powders and as well as the production of the gas and as well as production of your the additional post processing equipments which is required for AM processes. This will all relate to us the cumulative energy development or the demand, how much energy is required for our powder production or for the machine productions. It is what majorly important aspects in the when we talk about the sustainability of our additive manufacturing aspects. As majorly we are aware that like we think that this is most sustainable manufacturing processes, but as Professor Joshi has already told, we need to think of in what aspects the additive manufacturing machines are sustainable. Because some of the data they are given from some literature articles, I will just tell you, in the entire world only one manufacturers, that is the Renisha AM250, you are aware of that, the AM machine manufacturers, Renisha, Concept Laser, SLM Solutions and as well as the Beam. There are so many manufacturers are there, EOS Solutions, but Renisha has given only the data how much cumulative energy demand is required for the machine manufacturing. They had given us almost 124 gigajoule for the primary is required for, that is for the primary manufacturing machine 124 gigajoule, that is for the machine manufacturing, and almost 12 gigajoule is required for your auxiliaries. The auxiliaries means it is such as chillers are required. All our AM machines we need to have the chillers, because it has to be continuously cooling has to be takes place for our AM machines. Means that much amount of huge energy is required for manufacturing of AM machines and as well as for the chillers and all. But there was no other manufacturers like with respect to SLM Solutions or other additive manufacturing machines, nobody has given the data how much energy we are utilizing for manufacturing the machines and as well as for the auxiliary equipments and all. But this is going to give us lot of importance, because any part you want to print, how much energy consumption will takes place, because as we know that this is the most complex parts, we can easily fabricate it, easily build it, even which is not possible by conventional manufacturing process. That is the major beauty or the requirement for additive manufacturing process. But do you know that how much energy is required to print that part? Take for one example of your the additive manufacturing of the impeller part of aluminum. If I want to print aluminum impeller part, how much energy is required? Given the data, one of the authors, the for aluminum to make one impeller, they require almost of the 6 to 60% of the cumulative energy demand is required for the part. That depending on the size of the part, the cumulative energy means the size is again constant here, because that is again depending on the build volume of your machines, from smaller machine to the bigger machines. Again the energy demand is changing with respect to the build volume, because in the worldwide entirely we are having from almost 10 liters to 130 liters of maximum build volume we are having in the world in the additive manufacturing machines. But that is also having lot of constraints in the build volume aspects. To manufacture one like impeller, we need that much of 60% of the cumulative energy demand. But if you think of that, this is for the part manufacturing. Then again if you think of the powder manufacturing, again you think of the argon manufacturing, because these are all the two major feedstock for our additive manufacturing. One is powder, one is argon. These two are the major the feedstock materials, as Professor Joshi also told you, powder and as well as wire. But related to my talk, only I am giving you the important aspects of the powders and the gas, because gas is also a feedstock, because we need to purge the gas for the entire or PBF systems, or in the DED systems we need to protect over the beads. That is what the protecting gas we are using, or even the carrier gas for powder flow and all, argon for our titanium and more reactive materials and all, and for your stainless steel or ferrous based materials we use the nitrogen and all, and even some cases we use for helium as a gas for protecting media. That is what we need to think of. Even for the powder productions, people will say the global average cumulative energy demand for nitrogen almost 6 megajoule per kg. If you want to generate 1 kg of the nitrogen gases, we need required almost 6 megajoule. That much of energy is required. Then for argon they have told almost 38.6 megajoule per kg. Means if you want to generate that much of the argon gas, we need to spend that much of 38.6 megajoule energy. And if you want to make some kind of a powders, how you are thinking? Powder manufacturing, is it easier to manufacture? What are the kinds of manufacturing of the powders? Even today morning he has discussed how do we manufacture the powders. Like if you know that the powder manufacturing, most people are working with stainless steels, titanium, nickel based superalloys, and as recently majorly working on aluminum alloys and all, especially for additive manufacturing aspects. But for powder manufacturing, how much cumulative energy is required? Especially they are given in the literature data, because we need to use argon gas, the argon consumption almost 5500 liters per kg to manufacture the parts and all, to use for our atomizing the powders. If I want to manufacture 1 kg of titanium powders, I need to spend almost 5500 liters of the argon gas. Yield is going to be affect our environmental aspects, definitely. But when you comparing the conventional scenario, how much feasible, in what sense we need to think of which is going to be feasible aspects. And if you think, for example, the steel, they are given lot of different data, 18 megajoules, from 18 to 50 megajoules per kg of the steel powder productions for atomization aspects. And for titanium I told they are using 361 megajoules to 582 megajoules, 361 megajoules to 581 megajoules per kg of your titanium powder manufacturing. That much energy is required. and for per kg of your powders they required almost 5500 liters of the argon gas is required. And similarly for nickel they are having almost 114 megajoule per the gas, the energy is required for nickel based isotope. Means this is just the data I am giving you just to understand how we are to think of in what way the sustainability aspects, because the only aspect the powder productions and how we are making use of this powder production for our manufacturing aspects. Do you really comparing with the conventional aspects? Yes, even conventional machining aspect, how much energy consumption for machining and what are all the environmental problems we are going to attain, and what is the how the raw materials we are produced for manufacturing with respect to conventional scenarios. Then coming to these, the requirement of the powders or with respect to the cumulative energy demand, then how do we manufacture the powders? Are we in the today's scenario, because this manufacturing especially for the metal started almost 20 years back onwards. Since 20 years, are we really using the powders manufacturing from the ores? Because any raw materials you want to manufacture or produce or the extract, it has to be extracted from the ores. Are we really till today we are using the powders are manufactured from the ores? Then how we have to make use sustainable aspects? Let us discuss on those things aspect. This is the content I am going to tell you about this the overall lecture for the 2 hours. What is the aim trend? What are all the metal powders we are using, and we are discussing what are the powder productions majorly with respect to the scenario of atomization, because he has given the glimpse of powder manufacturing aspect today morning. We will go more in deep how the powder manufacturing or production is taking place, and as well as how do we characterize, because we know that the sphericity is important, flowability is important, but will the non-flowable powder particles are we using or not? How much extent we can use non-flowable powder particles? In what additive manufacturing we can use such kind of the non-flowable powder particles, and also the remanufacturing of the powders. How do we use reuse of your powder particles? And then what is the sustainable feedstock sources for your powder manufacturing, and as well as the effective powder management. These things we can discuss in this. Okay. If you see the AM market trend, since from 2023 to 2028, this is the projected data from the Oilers Association. If you see the cumulative growth rate, almost 16.1% the growth rate is the prediction, because this data has predicted from since last 5 years data how the additive manufacturing people are using with respect to all the scenarios. And if you see the AM market trend in terms of the powders only, this is with respect to the global market of the metal additive manufacturing process, and this is with respect to only with respect to the metal powders. If you see the scenario, the Inconel and stainless steel almost 40% of the powder growth is going to be taking place. In all over the metal additive manufacturing, we are mostly using stainless steel and Inconel, and now the development is taking place on the titanium, because of lot of qualifying components are using in our the aerospace applications and as well as medical applications. People are trying to use the 15 more than requirement for the additive manufactured parts in the aerospace and as well as for the medical applications. But if you see this research data has shown lot of the powder cost will be the highest continuous expenses through the life of a machines. As we know, for one machines additive manufacturing machine cost, we know that almost $20,000. The simple small machines we will get 1.5 to 2 crore of machines is required. That is depending on the build volume. If you want to have a 10 liters of build volume, you can go get it from that the 1.5 crores. But if you want to go the build volume size increases and as well as the multiple lasers if you want, then it will cost around 15 to 20 crores big machines capacity is required. Then will that really required? only the machine is there, that much big volume machine, can you directly use that part manufacturing for the applications, real time applications, or directly I can use that near net shape manufactured part into the ready to use applications? No, because we need to think of how effectively we have to utilize AM parts. Again we need to use post processing, right, and the post processing cost also will add up on the manufacturing cost of the part. And powder productions, are we using original powders, are we using reused powders? That will all come across into a part manufacturing cost. Then you need to think of whether that part is quality is consistent, because lot of challenges are in AM machines, AM part manufacturing. If you manufacture part from EOS solutions, or if you manufacture part from SLM solutions or from the Renisha, the part quality is different, because we are not getting the repeatability from different manufacturers to different manufacturers. Even though the process mechanism is same, they are using same concept of mechanisms, but our part quality is different. Then what is the challenges we are facing? Why do we are having this, the less in this repeatability aspects? Are that parts are qualifiable or not? Then is this mainly because of the powder feedstock? No, machines are 100% right. This is mainly because of the powders. Do you maintain the powders are used for all the machines are same? Is it from the same batch we are using the powders, or we are using from the different batch of the productions? Because even if you are using the same machines, if you use a one lot of powder and then if you use a second lot of powders, are we matching the same properties what we are used for the batch 1 or batch 2? That is also challenging issues are there with our AM machines. Then how to address all these aspects? And if you see that the global scenario for the powder market manufacturers, you might be aware that overall the powder manufacturers, the Hoganas, Praxair, and as well as the Sandvik, and even the 6K solutions, 6K additive solutions, and even in India, Indomim, and as well as some of the small scale companies, they have Matrix Nanos and all. These are all the global leaders for manufacturing the powders. Then if you see this, the growth rate with respect to the precious metals, more than 12% is growing, and with respect to the platinum materials 11.5%, and with respect to aerospace, that is on the super based alloys or on the titanium based alloys, it is 22%. And with respect to the titanium, it is almost nearly 30% growth rate is taking place since from 2021 to 2020. This is what the rate of the powder requirement in the additive manufacturing scenarios. Then how do we manage all these powder productions? Yes, we know powders are required majorly for the additive manufacturing process, especially for the powder bed fusion and as well as for the laser DD process. Apart from those two major metal powders, binder jet is also now moving more on to the powders, because these three major processes, if you see, this is the pie chart. If you understand here, we are using most of the powders for this material jetting, material wet polymerization, binder jetting, hybrid binder jetting, mode slurry deposition, metal laser sintering, or electron beam powder bed fusion, or maybe the laser beam powder bed fusion, laser electron beam, powder laser DD deposition, and as well as for the cold spray technologies. For all these AM technologies, we need the powders. Then if you see the growth rate 8% in 2024 to 36, and as well as what are all the growth drivers, that is what the surgical increase in the demand of automotive industries and as well as for the aerospace industries, the market, the metal powders growth is taking place. That is based on this region wise with respect to the Asia and as well as with respect to the North America, we are having this much of the growth rate. That is also with respect to the ferrous and as well as non-ferrous materials. Majorly we are growing with more on ferrous based materials with respect to this. As I told you, the most leading manufacturers for these powders are Hoganas, GIAN Aerospace, and as well as the Sandvik, and as well as American Cement Corporations and the Carpenter. These are all the leading manufacturers for our powders for the IoT manufacturing. Then even today's morning professor told we need to choose from which manufacturers we need to buy the powders, because if you buy the machines from 3D systems, 3D systems will tell you need to buy the powders from 3D systems only. Yes, but can't we use any other powders for the 3D systems machines? They are telling whatever the process parameters we are given to 3D systems for printing the stainless steel materials will not work if you buy the powders from other systems. Is that the real scenario? No. Because we need to think of how the solidification is taking place, how your laser and powder interaction is taking place, and what is the process conditions we are using for the printing aspects and all. Right, if you see here, hence we need to understand the quality of powders which we are using for our IoT manufacturing process, who is the supplier, and whether it is in original condition or in the reused conditions. In majority scenario, in the Indian scenario, what we are buying? We are buying the powders even sometimes from the local manufacturers. Like you might be, as I told, the Indomim are most leading manufacturers for the injection molding parts and all. They are also producing the powders especially for the powder metallurgy aspects, because as powder manufacturers can only segregate the powders which is required for coating, which is required for powder metallurgy, which is required for IoT manufacturing. They cannot go only for IoT manufacturing aspects. Even some of the Chinese powders, Indian scenario we are getting, but will that the original powders, or it is a reused powder? Again they are using spheroidization techniques or atomization techniques to make it spherical, make it to improve the flowable properties and sending into the Indian scenarios. From these powders, are we getting a good quality of the components? Then whom we have to blame? Whether the powders or whether we have to blame the machine. Then we need to have the challenging issues, repeatability and as well as the mechanical properties what we are getting after printing the parts. Is it because of the powder defect or because of the machine variations? That is what we need to understand, whether the powder is what quality it is. And then that is the quite challenging for any beginners, any new IoT manufacturing machine manufacturers as the researchers. That is the major challenges. How do we decide the powders from which suppliers we have to buy, whether from the US solutions or from the Praxair or Oganas or maybe Carpenter, Sandvik, ATI or Tecna. These are all the worldwide suppliers. Everybody will supply the powders, but they are not meant only for our IoT manufacturing. Leading powder manufacturers for thermospray coating, powder metallurgy as well as for IoT manufacturing. They are just only segregating the powders which is required for different processes, right. Then are that powders are validated? Are we using that validated powders? Is it suitable for the use in the IoT manufacturing process? Then how do we choose, how do we validate these powders for IoT manufacturing process? And that which list the validated powders can de-risk of procuring the powder for AM. It does limit the under the signal the sources of the suppliers, inhibit the development of in-house expertise. Means anyone cannot buy the powder from the market. You need to understand how powders are manufactured and what powders we are using for IoT manufacturing process. Because techniques we have gas automation, we have plasma automation, we have plasma rotating electrode automation process. These process methods will give us the powders are manufactured by automation, but when you think of this the process of automation, we have this the many methods, that is what in the automation techniques, the gas, water and as well as the plasma automation. Again in that plasma we are having plasma routing electrode automation and then spin off methods. There are different techniques out there. But if you see here in the gas automation, whether we are using argon or whether we are using nitrogen, and in the water we are using water atomization, which is followed by the oxide reduction under hydrogen atmospheric conditions under. But when you use these kind of techniques, what properties are widely depending on the automation techniques and how the manufacturing conditions are takes place. Means if you think of which powders we need to select for our AM, this is what the process conditions for automation, and then the importance of the powders, why the powders are important in our manufacturing scenario, and routes of powder productions and the powder recycling. Means how powders are important in additive manufacturing. If powder quality is poor, then whatever you play in your process conditions in manufacturing the part and all, ultimately you will end up with a poor quality of the part and all. That is why the important is the powders. And then we need to understand what is the roots of this powder productions, how it is manufactured. Is it manufactured directly from the ore or from the ingots or from the reused powders or maybe from the scrap. That is what we need to see, the roots of the powder productions and then powder recycling. If you see the importance means how critically influences on the final component properties, because we know that in the DED or in the PVF systems we have discrete amount of the powder feeding in the hopper, because in the PVF powders will be dispersed on the build platform area, but in the DED systems powders are feeding into the feedstock to purge into the coaxial nozzle or bidirectional nozzle, whatever the nozzle arrangements will be there. That will be fall on the focal point, it interacts with your laser, then melt pool will form in the flight and then deposit a bead. But in the powder bed, your compacted powder will be there by the doctor's blade or by the roller, then you will be having so much of packing factors. We expect one packing factor, but that not going to be a one factor. Depending on that factors ratio, we are going to melting and solidification is taking place. Apart from the process conditions, the powder quality is also a important aspects. Is that powders are homogeneous distribution is taking place in the build platform area. For that we need to have the Gaussian distribution of the powder particles. That is what important in the Gaussian distributions. If you go with too much of powder pooled in one area, what will happen? Definitely the laser will interact with that one pooled powder particles and it won't melt properly that pooled powder particles. In some area if your powder is not dispersed properly, then it will melt, it will create so much of the empty spaces. That is what the pores are going to create. This is the problem will be there if you are not having homogeneous distribution of the powder particles in the build platform area. That is we need to understand the importance. That is what the powder performance in AM, how much layer spreading, hopper dosing or the bulk packing depending on the properties, and as well as the build efficiency and the unused powders and the cost factors. Means the build efficiency means is that the actual component volume is significantly less than the total powder spread, because if you take 100 by 100 mm of your build area, we are spreading entire build area for powder particles, but will that we are using entire volume of a build area for the manufacturing the part? That is dependent on the what part we have designed and how much area of melting is taking place. We cannot use 100% of the build area. That is also with other constraints and the build defects what we are failed in the printing scenarios and all. But then unused powder, for example, if you build 100 by 100, then if I print only a 10 mm part in that build area, how much part we are losing, how much powder particles we are losing. That is what the large amount of the powders remains unused in the build after the printing. And the cost factor, given that highest cost of the metal powders, effective recovery and as well as reuse of unused powder essential, because it should be essential, because we cannot buy every time new powders for printing the part and qualifying it, because that will lead to a lot of cost of manufacturing in the part. Then how do we have to manage, how much times we have to use this reused powder for printing of parts and all. Directly can we use this unused powder for the printing? We cannot use, because it may change the surface properties because of the oxidation, or it may change because of the thermal properties. There is a slight heat absorption taking place by the surrounding media, or reacting with the reaction of the gases during the melting aspects, and also maybe agglomeration in the surrounded powder particles, or some satellites are sticking onto the surrounded powder particles because of the melt pool ejections from the solidification and melting. With all these criteria, we need to think of how to use unused powder particles in the build platform. Again we have to receive, and then we can think of how much quantity of powders we have to mix with your original powder particles. I have original powder particles 60%, and then 40% of the reused, that is what the sieved powders I can able to mix with the original powders. Then what is the cost factor? That is all depending on how much efficiently we are recovering and reusing our powder parts. And if you see the roots, that is from directly from the ore, we are extracting and then forming the ingots, and that ingots are used for our automation process, either the gas automation or water automation or centrifugal automation process, then to make the powders directly from the ore, right. And then if any hydrogenation or dehydrogenation, that is generally using for our titanium powder particles and all, we are reacting with that process is the titanium oxide or titanium hydride, then we can extract directly titanium powder from the titanium hydrides. That is what the hydration and dehydration. This is what the stages of the powder production from the ore. But are we really following these kind of the process for the till today? That is what we need to understand, how much efficiently we are using these powder productions. And if you see this, as I told, atomization, then how this automation process works for the powder productions. In these automations, any material which can be weldable, which can be possible to melt, which can be able to make the powders and all. That is what the breakup of liquid into a smaller droplets, it is called the atomization, typically into a range of 150 micron, means less than 150 microns, whatever the particles you are producing from the billets or from the ingots, that is called the powder particles by the automation process, right. But that how do we process this automation? What is the mechanism of this automation? You see this the mechanism of automation, stage 1, stage 2 and as well as the stage 3 and stage 4. Means in the automation chamber, if you see this is the big automation chamber, either vacuum or argon automation chamber, we are purging our molten pool materials or the ingot materials, and that it will drop down and we are impacting that with a high velocity, that we are disturbing that molten pool with a very, very high velocity of the water or by the gas. With that what will happen? It will create a sinusoidal wave in that molten pool. That is what in the stage 1 the wave is going to create the sheet of molten pool, that is in the stage 1. Then that powders are going to as a fragments or the ligaments are going to form in the stage 2. In the stage 2 it will break that sinusoidal wave into a ligaments, and then that ligaments further it will break down into a droplets. That droplets are going to create as a in the stage 4 in the automations as a small particles, that small particles are collected, will that have a size reductions by the limited viscosity or temperature or the acceleration forces. With these the stages of mechanism of powder particles are going to take place in the automation process, either water or either gas automation process, right. If you see, this is what the big industrial automation in the argon going to take place. And if you see the process of water automation, as I told, all the mechanism is same. We are purging our liquid molten materials into the automation chamber. This is the complete automation chamber. In the stage 1, with high impact velocity of your water droplets, we are impinging with very high velocity to create the sinusoidal wave that will break down again into the ligaments and as well as the particles of the powders. And how do we control this? Can we able to control? How we can able to control the powder particles, either in the gas automation or in the water automation? In the water automation, we are impinging with very high velocity based on this, the nozzles of the water inlets. But in the gas automation, we are purging with respect to a high amount of the gas in this nozzle area. And all this we can able to produce. Then when to use this water automation and when to use this gas automation process? Then what is the problems we are facing when we use water automation and as well as gas automation process? If you see here in the gas automation process, we can melt and we can feed the powders less than 120 kg per minute, and we are going to get the powder particles in the range of, I think, 100 to 500 micron size. But when we melt this, how do we control the powder particles? What is the rate of impingement? Whether you are gas or whether you are water, in what rate we are impinging into that molten pool, and as well as the velocity, and what is your orifice angle, that is how much water inclination is falling onto your molten pool. With this we can able to control the formation of your diametrical of the powder particles. That is what, if you see the two differences here, the D50 is 200 micron and D50 is 29 microns. The major changes is here only the gas impingement, how the gas impingement takes place onto this molten pool and all. That is what we can able to produce. If you see in this scenario, we are getting less than 45 micron, only 5%. But in this scenario, we are getting more than 70% of the 45 micron powder particles we can able to get. That is by altering the impinging angle and as well as the velocity. This is what we can able to easily control with these scenarios, right. And if you see in the recent developments were taken place by the 6K additive solutions, that is what vacuum induction automation technology that means especially for our the titanium powder manufacturing process, because in the titanium we are generally using for the argon, because titanium is highly oxidizing materials, it will quickly create the titanium oxides. Because of to protect this oxidation formation, we have to use either the vacuum chamber or we have to use a argon atmosphere conditions, right. And how do we control? As I told, if you see with that velocity, we can able to control the particle diameters. Means if you see this, the geometric constant with respect to the acceleration gravity and how much amount of the injection of the pressure onto the molten pool and as well as the pressure onto the automation gas and as well as your density of the liquid molten materials. With that we can able to control the ligament forming into a spherical droplets. With these we can able to break and control the formation of the powder particle diameters, right. And how the evolution of the microstructures? Okay, the powder particles are break into ligaments and then droplets. In our additive manufacturing process, we are going to get columnar dendritic structures, but will that follow the powder particles? Why we are having these kind of the dendritic structures? What is the major scenarios with respect to this? Because of the rapid solidification, means when rapidly solidifies these powder particles, it will create that the crystallographic directions are growing towards solidification in all the directions. With that, if you see that that is depending on the lambda, that is the dendritic column spacing, which is equal to the kT to the power of n with respect to the material constant and with respect to the cooling rate, and n is the constant with respect to the materials. Means if you understand how the dendritic column spacing, whether the primary or secondary dendritic column spacing is going to form, which can able to correlate how the solidification is taking place, what kind of the powder particles or microstructures we are going to get it in our additive manufactured powders and all. This is mainly because of the rapid solidification is taking place, means the freezing of your solid liquid interface is more enriched with your the liquid and solidification growth also. And if you see the different morphology of your powder particles, if you see the water atomized, chemically induced, and as well as plasma atomized, mechanically allied. What differences we are observing here comparing with your gas atomized powder particles? See, as I told, water atomized you are majorly using for the ferrous based powder particles, because it is not much oxidative, directly it can use, not much oxidation is taking place. That is what we are using water atomization for the ferrous based powder particles and all. But the powder particles which are more reactive to the atmospheric conditions, we need to go with the gas atomization or plasma atomization process. And also another scenario, if you see here, water atomization powder particles are not highly spherical. Non-spherical powder particles also we can be able to get it, because this is depending on the solidifications. In the water atomization, rapid quenching is taking place comparing with the plasma atomization process. The rate of cooling is different in the gas atomization as well as in the water atomization. Because of that, you are going to have some kind of irregular powder particles also going to get it solidified. And in the chemical reduced process, that is like a just spongy like structures, we are going to get it in the chemically produced powder particles. By the chemical reactions, we can able to extract the from ore to the powder particles. Those powder particles are not like a sphericity of the shapes. Then in the plasma atomization, if you compare with this gas atomized and the plasma atomized are more spherical powder particles, because in the plasma atomization we are using a plasma channel to melt the filament of a wire, the ingots, and then solidification is taking place by your argon gas. We are not pouring the molten pool into the automation chamber, with controlled velocity of the feeding of your feedstock materials, and then with the help of this plasma you can able to control rate of solidification and the formation of the sphericity in the plasma automation. That is why we are getting a very good spherical powder particles. This is the powder particles are much suitable for our additive manufacturing process, but we cannot able to afford this much highly spherical powder particles because of the cost of manufacturing. That is the thing, we are using this gas atomized powder particles and as well as water atomized powder particles depending on the requirement aspects. Either simple parts which are not highly required for your aerospace applications, then no need to worry with your water atomized powder particle. Yes, it will definitely flowable, and it could have also the compaction ratios and also the packing factors. The packing factors mainly by the distribution of your powder particles. That is what we are using for DED process, 45 to 110 or 45 to 90, and for PBF we can use 5 to 45 or 15 to 45. That is what the distribution of the powder particles we are using. Based on this distribution, we are having a packing factors. Then if you see the mechanically allied powder particles, that is by the mechanical crushing, ball milling, attrition, we are having these kind of very irregular powder particles. These irregular particles are suitable for additive manufacturing? It is not suitable, but we can make use of these powder particles also by our laser direct energy deposition process. But these kind of powder particles are not suitable for PBF process, but we can use these powder particles for the trial testing to qualify the powder particles or qualifying melting and solidification of the aspects. For developing some kind of new alloys or new ceramic powder particles or new metal matrix composite powders and all, in such scenarios we can use mechanically alloyed powder particles can be used for your qualifying aspects and all. That is how we can make use of the powders with respect to the different manufacturing scenarios. And if you see the, as I told, the solidification and microstructure, how you are evolving your microstructure in your powder particles. That is, if you one nuclei will start to grow at random locations, like that individual powder particles, multiple nuclei will be there. That multiple nuclei will start to grow in random directions, that is going to create your dendrites in all the directions. If you see these kind of the, in a one single powder particles, we can expect these kind of the solidified dendritic microstructure in your powders. But all these powder particles, how do we understand, how do we characterize this? These are all the microstructures of your powder particles, the morphology and the microstructures. But these dendritic corner spacing can be controlled by your solidification rating. That is what I told you here, the lambda is equal to K2 to the power of n, that is dendritic corner spacing is depending upon the solidification rates. If you see the copper alloys or the austenitic stainless steel or for the aluminum alloys, the dendritic corner spacing is different with respect to the solidification rates. With that we can able to control our the solidification rates to get the different kinds of the dendritic corner spacings and all. Okay. And regarding that plasma dimension, I told we are getting very spherical powder particles. Why do we get that spherical powder particles? Because here we are feeding the filament in the form of a spool of a wire, and with that plasma torch we can able to melt with a controlled amount of the molten pool materials, and then we can able to purge into a high amount of the argon gas to get the required particle sizes and all. That is what possible in our automation chamber. But the cost of manufacturing with respect to this plasma automation is going to be very, very high, because we need to maintain the plasma channel and as well as complete automation chamber. Especially these plasma automation we are using for titanium powder particles. That will be very, very low yielding capacity, because do you think that to get 1 kg of titanium powders, how much tons of metals we need to melt? Because we wanted to get 1 kg of powders, for PVF powders at least we need to have 5 kg of powder particles to build 100 by 100 volume for maximum of 10 mm thickness. To produce 1 kg of powders, hardly we have to melt 100 kg of molten materials, because we are not going to get highly spherical powder particles, irregular particles, nanoparticles, less than 5 micron, greater than 45 microns, all this has to be segregated. Only we are using in the range of 5 to 45 only for our PVF process. Then to produce only 1 kg of powder, that much quantity of powders material, molten metals we have to add, that is what you are having a very, very low yielding. It is only hardly 5 to 6% of the entire amount of materials yielding into a small amount of powder particles. That is what high powder cost and the limited capacity. That is what in the plasma automation it is having a high powder cost and as well as limited capacity. And if you see, this is what the advanced titanium automation was developed by the 6K additive solutions and all. This is what the ingot in the complete chamber liquid metal, and it will melt and it will form as a supersonic gas structures, and then pulsating it is going to create as a ligaments, and that ligaments going to form as a droplets, and then that droplets will solidify, and in the container it is going to be as a powder particles. Then it will be sorted by our different kind of sievings and all with the different types of meshes and all. This is what the recent development by the 6K additive solutions. If you see, this is the like how much in the world the titanium atomizers will be there. That is a very big machines, even it will be more than industry big machines will be there. It will, because we cannot produce simple 5 kg or 10 kg of powders in one lot. At least they are going to produce in terms of 5 tons in the one automation techniques. That is why the cost of manufacturing is very high in this automation techniques. And the hydride and dehydration techniques, this is another kind of powder manufacturing, that is what especially we are using for the titanium powder manufacturing. If you see, titanium is reacting with chloride, initially it will be in a titanium chloride, then we are dissociating chloride separation by the sodium reduction. With that sodium reductions, it is going to form as a sodium chloride, then you are ultimately end up with a titanium, that is going to be dried with your atmospheric conditions to get this titanium. This is what one of the hydride and dehydration techniques which is majorly used for the pure titanium powder productions and all. Okay. We will stop this, and further we will continue with respect to the where manufacturing usage, how do we characterize, and then how we can think of the sustainability aspects in our manufacturing with respect to industry scenarios and all. Okay. We will have a break of some 5-10 minutes, then we will continue back. Okay. Manufacturing methods for the powders. Are we really using for all the powder manufacturing methods for the additive manufacturing? No. But if you see in water automation, we are getting in the range of 0 to 500 microns. We can get in one water automation techniques that much range of the powder particle sizes. What will be the advantage for this water automation? We are having a high throughput, range of particle sizes, and it will require only a feedstock in the ingot form. We are using a feedstock in the ingot form. But what is the disadvantage? It may be contaminated with moisture because of the water atomization, and another is it is also a irregular powder particle distributions we are going to get it, and that the particle size distributions will containing have a satellites. That is what we will be having more amount of the satellite powder particles are there, irregular powder particles, and as well as satellites will be there in the water automation. That is the major disadvantage for our water automation techniques. And we will be having a low yield of powder between 20 to 150 microns. Yes, we are getting 0 to 500 micron powder particle sizes, but the yielding capacity for 20 to 150 micron is very less. That is the major disadvantages of this water automation process. And this is mainly used for non-ferrous, non-reactive materials, that is what the ferrous based materials. All the stainless steel based materials we are using the water automation techniques. And for the gas automation, again we are getting in the same range of 0 to 500 microns. This is we are having very much suitable for the highly reactive materials, that is what the titanium, aluminum, super based alloys are most suitable for the wide range of gas automation process. Here it will be used for the high amount of throughput and as well as the rate of the particle sizes. And very spherical powder particles we are going to get in this water machine, and satellites are present, but it is a very small ratios, and also will be having a wide range of particle size distributions. And here also the yielding is very low in the range of 20 to 150, and this is majorly used for nickel based alloys, copper based alloys, ferrous based titanium, and as well as aluminum and cobalt chromium alloys and all we are using gas automation process. And for the plasma automations, the range has come down, the particle size distribution range has come down from 0 to 500 micron to 0 to 200 microns. Here we are getting extremely spherical powder particles, and the major thing is it requires a feedstock in the form of a wire or in the form of a powders. We can use water atomized powder particles or gas atomized powder particles as a feedstock for our plasma automation process, or also we can use your welding filaments. The wire spools also can be used as a feedstock for your plasma automation process, and this is majorly used for our titanium alloys. because we need highly controlled atmospheric conditions for titanium. That is why we are using plasma automation is the very much suitable process for the titanium powders. And the another one is plasma rotating electro automations. There we are getting still further decrease in the particle size distributions. 0 to 100 microns we can get high purity, highly spherical powder particles, we can get it, but the powder production is very very low. That is what low productivity and high cost, it will be used for titanium exotics. And for the centrifugal automation, the range has gone 0 to 600 and wide range of particle size with narrow particle size distributions. The size of distribution is very very narrow and we are getting wide range of particles, and difficult to make extremely for the fine powder particles unless very high speed can be achieved. That is what how much your disk rotation, the centrifugal disk rotation, based on that we can able to control the size distributions. That is the major difficulties is there. To get the fine powder particles, we need to think of how much the particle centrifugal rotation of your disk, based on that we can able to control or achieve our fine powder particles. And the extremely using for the zinc alkaline batteries powder particles are pastes and all, and as well as the titanium and steel shards. For this purpose we are using centrifugal automation process. And the another one I told you, the hydration and dehydration process, we are getting 45 to 500 micron size of particle size distributions, and as well as it is of low cost of option. To get it into a very very minimal cost, we can get low cost, and will be having irregular powder particles and is having high interstitial content of hydrogen or the oxygen content, because it is name itself defined as hydration and dehydration. Because of that, the hydration and dehydration process contaminated with the hydrogen or the oxygen contaminations. This is limited to metals which are more brittle in nature, and especially we can use for titanium also. That is what with respect to the powder manufacturing and its advantages and its uses for the EM processes. And if you see what is the key point variables for this powders and as well as techniques, will that could be used for their measurements. What are all the key variables means? The major key variables, the shape, morphology of your powder particles, whether it is spherical or non-spherical or it is irregular powder particle. That is what the shape will going to give us the whether it is spherical or not. Then how do we justify, how do we characterize this whether it is spherical or not? Means one way we can go with optical microscope, or we can analyze with the scanning electron microscope. That is what the assessment techniques will give us. We can able to assess the morphology of the powder particles by SEM and optical. And if you want to understand the size distributions, how do we analyze the size distribution or the particle size distributions? Means how do we sort out these powder particles? By your sieving process, different kinds of the sieves we can use to sort out these powder particles, either by mechanical sieving or by laser diffraction or by optical microscopy. In mechanical sieving, we can just segregate the powder particle sizes, but we cannot say what is the distribution. Is that how much D10 powder particles, D50 powder particles or D90 powder particles? Means 10 diameter particle how much distribution, or 50 diameter how much, or 100 micron how much. That we cannot able to segregate in your mechanical sieving. Just you can bifurcate the powder particles by mechanical segregation. But if you use that small quantity of powders for your laser diffraction or optical microscopy, we can say how it is distributed. That is what distribution of powder particles. And the particle porosity, can we able to identify particle porosity? Powders are manufactured by water or gas automation. If powder is having a porosity, how can we analyze, how can we characterize it? By NDT techniques, or by the X-ray CT chromography, or by the optical microscopy. Optical microscopy or with SEMs only if it is having a surface porosity. If porosity inside your powder particles, then we need to go with a non-destructive testing only. That is what X-ray CT is the best way to analyze the porosity inside the pore particles. Okay. And the another, these are all the particulate properties, and the other one is the bulk properties. Bulk property is the density, flowability, cohesiveness, and as well as the surface area and the chemical composition. These are all the bulk properties of your poured particles, because these key variables are very much important in the additive manufacturing. If you are having less operant density or low flowability or low cohesiveness, then your chemical composition is changing, then it will be affecting your quality of power part which is manufactured by additive manufacturing. Then all these things, how do we analyze? See, one by one we can go through that. This is what the powder particles, hydration and dehydration process, plasma automation, gas atomized, and plasma routing electroautomation. If you see highly spherical powder particles, we are going to get it in plasma automation, plasma routing electroautomation. In plasma automation, the another challenge is very fine powder particles or spherical powder particles that has to be bifurcated. But in plasma routing electroautomation, we are getting highly spherical powder particles of a required distribution sizes. That is what we can get it in the plasma routing electroautomation process. But if you see this size, one is from Trueform or from the Praxair or from anyone, we need to control the melting, and then we need to understand the morphology and what is the solidification rate, how much level of your impurity, whether it may be the titanium oxygen contamination or maybe the nitrogen contamination. Any powders if you buy from the suppliers, we need to think of all these properties, flowable properties, distribution sizes, how much oxygen contamination and nitrogen contamination. It should be less than this, the 300 or 500 ppm in your contamination of the powder particles. Because if you do not think of these things, then ultimately you cannot able to justify the defects or the low properties in your mechanical caused by your powders or by your process conditions. That is why we need to buy a highly qualifiable powders by analyzing all these process conditions or the characterization aspects. If you see, I told you powder characterization can be done by particle size distribution, the impurity with ONH or the CS, or with tap density, alflometers, FT4, ganogram. With microstructure we can do with SEM or mechanical etching or optical microscopes and all, or with your confocal microscopes and all. And property measurements, that is what the hardness, tensile, high cycle fatigue or profile photometry or indentation or phychrometry or Archimedes, all these are all the properties. And even you can go with the heat treatment aspects. We are using all these techniques to qualify our powder particles. Even we can analyze the hardness properties of your powders. Means those are all very much important, the morphology and characterization of the powders and all. And if you see the particle shape and shape factor, will that majorly influence your characteristics? Because we cannot quantify, because if you buy 10 kg or 50 kg of powders, we need to test only one lot of powders. We will just take the 100 gram of powders just to analyze these characteristics, flowable properties, particle size distributions. We cannot take all the 10 kg of powders to analyze it. Are we ensure that this entire 10 kg of powder particles going to behave same powder properties? Then how do we analyze these powder particles? Because we need to think of how much quantity of powder particles we are taking from the surface or from the middle or from the low. Because if you take the quantification analysis, we need to take from one lot maybe producing 10 ton. In that 10 ton, from all the aspects they have to take the powders and they have to measure. Then they can able to see for this lot, this is what the characteristics. That is why we need to analyze all the shape and as well as its shape factors. Usually it will be described by the ratio and the shape factors, the aspect ratio and the shape factor. And aspect ratio is the ratio of the largest dimension to the smallest dimensions. and ratio ranges from spherical to the flake, irregular flake like structures to the spherical structures. That is what gives us shape of the powder particles, and that shape factor is also called as a shape index. We are expecting very spherical powder particles. That will give us how do we measure the ratio of the surface area with respect to the volume of your powder particles, and the volume is normalized by spherical powder particles with respect to the equivalent volume. Will that shape factors of the flake is higher than the spherical powder particles. All these are all relating our flowability aspects. If you see the flowability, as I am telling, when the metal powders are being filled into your die, it should be easily flowed and as well as compacted. That is what gives us flow. Compressibility means when you are applying load onto that, the poured powder into a container, how much extent it can able to compressible. And density, when we come to the density, because bulk density is different, theoretical density is different, apparent density is different, then as well as grain density is different. Then how do we qualify the density of your powder particles? Because if you take titanium, density is 4.5. Will that powders will also having the 4.5 density? Then how do we measure the density of your powder particles? Then density we are going to measure by using different things. That is what the flowable properties, grain density, apparent density, and as well as packing density. But when you think of this characterization or the analysis of your powder particles, especially which is required for your additive manufacturing 45 to 110 or 106 or 15 to 45 or 5 to 45 microns with respect to the depending on EM processes, we need to characterize these things. But as I told, by SEM we can able to analyze the morphology of your powder particles. But if that powder particles microstructure or porosity, we need to analyze only by the mechanical aspects or by your using a X-ray CT tomography and all. But the cheapest method is we can put that powder particle in the mounting and we can do polishing to reveal this kind of a structure, and we can use this polished single individual powder particles under the microscope, optical or by SEM, can able to reveal the shape or any porosities are there or not. But what is the problem? If you see that sphericity is good, but still we are having roughly embedded powder particles or epoxy on the surface area of the powder particles. And sometimes what happens, these powder particles are not easily able to absorb by your electrons. That is why we are doing some kind of a coating. That is what sputtering we do, gold sputtering or any conductive sputtering we can use for coating of your powder particles, and then we can observe in our SEM, can able to see the powder particles morphology and all. But if you see, we have done some kind of a electroplating onto this the nickel powder particles with a tin coating, and just to reveal that how the shape and morphology. If you see that backscattered image and as well as secondary image will gives us the microstructure, how sphericity of your powder particles, and in the cross section does it having any kind of porosity or not. This is the simplest way of analyzing the powder particles. If you coat this electroplating with nickel, with tungsten and all, you can able to see the sphericity and as well as improving approach of particle size analysis. If you see these powder particles and as well as this powder particles, both are same powder particles, you have done coating with the nickel plating, optical microscope. After mechanical polishing, you can get more the edge. Scanning electron microscope, we can able to see only the porosity is visible in the surface. How much depth, what is the volume, we don't know. For those things we need to go with the X-ray CT tomography only to understand the volume aspect of your porosities. Okay, this is what need to understand how much volume. If you see, this is what the porosity in your SEM, but in this one we are not seeing any porosity, only at these locations and as well as these locations. This is what in the SEM we can able to observe, but in the CT we can able to get the volumetric porosity of your individual powder particles. This is what I am telling with respect to only single powder particles. If you take the small quantity of 5 gram or 10 gram of powder particles, undergo with CT scan data, then you can able to get how much volume of your porosity existing in your individual powder particles. Because these are all very very important aspects when we use these powders in your IT manufacturing. Because when we have cracks, when we have porosity, lack of fissions, we need to understand this is caused by our process induced or porosity induced or powder induced, or it may be a lack of fissions. Because these challenges are going to be taken place when we are buying a very very highly qualitative powders. Need to understand these things. And if you see, some of the researchers have worked on this, the pure original powder particles and reused powder particles. If you see, this is the pure powder particles and how the microstructure with Inconel, titanium, aluminum or the scam alloy and all, and this is what the reused powders. What will be the problems? One is with respect to the change in the morphology of the powder particles. The surface remelting has taken place. If you see, this is what the surface remelting in all the aluminum or in the titanium powder particles, because titanium is highly oxidizing, it may contaminate the oxygen or it may be agglomerated. See, when we say the agglomerated, the surrounded powder particles are sticking onto the surface of the single powder particles. These called agglomerated powder particles, which cannot be used for our AM process, because it will be obstacle for the flowability and as well as packing factor. Then how do we break these agglomerated powder particles? Again we need to go with sieving deagglomeration technique to break these powder particles. Again we can re-sieve and go with some kind of a automation techniques or mechanical process to break these powder particles. Again it can be used for our IT manufacturing process. And that particle shape, that is what the aspect ratio with respect to shape, and the shape factors and the size distributions. As I told, the size distribution we can able to analyze in the particle size distribution with laser interferometry or with optical microscopes. With that, even with optical, we need to go with some kind of image processing analysis. That is what with the image processing we can able to see. With different color coding we can able to get what is the sizes, what color powder particles are there. With that we can able to plot the size distributions. This is with the simple image techniques, or even you can write simple MATLAB coding, we can able to analyze this kind of morphology with the particle size distributions and all. And even the standard techniques are there, particle size distribution techniques with the laser interferometry, we can able to get these kind of the normal distribution curve as well as cubed with left or right with the cumulative distributions. When we say this kind of distribution, your powder particles are distributed in one way, right side cubed or left side cubed. Means we are having more amount of the powder particles above 50 microns. That is what the right skewness and the left skewness. But we require for IT manufacturing, we should have the cumulative distribution of the powder particles as a normal distributions. This is what we need to understand and we need to analyze for our IT manufacturing aspects. And if you see that powder particles, if this is the case, this is what used with X-ray instruments with laser interferometry. They have got these kind of particle sizes. Will that powder particles are sufficient for IT manufacturing, either PBF or for the DED process? We can use these kind of powder particles, but here the more amount of powder particles, the distribution or the frequency is 0 to 20, right. If you see that 20 to 100 microns, the frequency or the fraction of powder particles are very very less. Means we can use, then what happens, the packing factor, packing ratio is going to change. Then we may expect so much of porosity or voids in the fabricated part or the printed part in your IT manufacturing. That is what we need to use. We need to have a high amount of packing factors. We are expecting to one at least 0.9 or 0.99 or 98, that much packing factors we are expecting with the normal distribution of your powder particles. The another aspect is, as I told, Reused powders, what happens? One is agglomeration, one is contamination, and the oxidation. If you use titanium powder particles, original powder particles is like this, and if you are used powder particles, it is contaminated surface oxidation. This is with mapping with the electrodispersive mapping, you can able to analyze EDS to get this kind of oxygen contamination. Like this, each individual particles, if it is contaminated with oxygen, then it is going to have a surface titanium oxide. To break that titanium surface oxide, we have to use more amount of the melting energy, more than the what it is required for titanium. Then we are going to use creating the process induced porosities, because we are melting, over melting the titanium powder particles. To break your titanium oxide, it will create your porosity by the process induced. That is one kind of the problem we are going to arise. Then another aspect is the cohesive strength. How do we analyze this cohesive strength? Because the powder particles, will it easily flow or will not? If you are using a alflometers like this, different kind of alflometers are there. With this alflometers based on the ASTM standard 214 and as well as with respect to the 213 standards and 417 standards, we are analyzing how powders are flowing. We are taking 50 gram of powders based on the standards, and with this conical funnel of 30-degree inclination with the hole diameter of 2.5 mm or with respect to the hole diameter of 5.4 mm. And we are using this kind of Carney flow for our aluminum powders, which is not easily flowing aluminum powders. Those powders which are easily flowing, we are using a alflometers. With these things, we can able to analyze how your cohesiveness of your powder particles. Means when you use these kind of flowable measurement equipments, if you are forming these kind of cohesive arc, then if you take small amount of powder particles in your PAM and compress it, if you release your PAM, will it be holding a same shape or not? If it is having a hold same shape of your PAM, how much your compressing load is applied, then your cohesive strength is low or high? It's very high. Then that kind of powder particles, if you are using, it will not flow easily, because it is attaining your more amount of cohesive strength. It should form easily flowable, means it should not retain the same shape when you are applying load onto it. That is what easily if you are flowing, it may create some kind of rat hole also, because these two kind of powder particles are not suitable for our additive manufacturing. For these two powder particles, we need to apply some kind of a load or pressure onto the flow of powder particles. That will create your this kind of rat hole or cohesive circular arc in your the outlets. If you are using these kind of powder particles, then you are end up with the defects in your part fabrications because of these properties. Then what are the other factors which are affecting the apparent density? Then how do we measure this apparent density? Apparent density is with respect to the mass by volume. That is what we are using. Then the mass of the powder particle density which is holding in your cup, that is what in the 50 gram, and how much volume of density of your cup with respect to the alflometer, it will give us apparent density of the powder particle, which was measured by your ASTM standard 212 standard. Okay, this will give us how much apparent density of your powder particles. And also we need to make sure will that powders is a contaminated or oxidized, or we are applying any tapping or vibrations. That will give us how much amount of the moisture contamination, that is what the humidity, then it will lower the density. Means we need to understand all these aspects, as professor already told, because in different area we are having different moisture contaminations. If you go to NIT Surathkal in the seashore, you will be having more amount of moisture content. Even though you are packed in a proper manner, vacuumized or sealed in containers, it will be contaminated with moisture. Such kind of powders will be definitely having a low flowability. Then we need to preheat, then to make it remove the moisture contamination, to use that powder particle for our AM process. Okay, but in dry areas we are not required such kind of moisture removal and all. And the particle size distribution, if you see the atomized powder particles, the average particle also going to affect your apparent density. Means if you are thinking that the size of powder particles is 5.8 to 18, then if you see here the apparent density is changing with respect to your particle sizes. 5.8 your apparent density is 0.62, then if your size of particle is 18, then your apparent density is 1.09. Means the size is relating to your apparent density with respect to all kind of your powder particles. And then how do we measure this true density? The true density of your powder particles we are measuring with these kind of a picometers. That is what with general techniques we are using with the flow well of your gas, and then we are containing with the reference volume of your powders, and with the sample holders how much powder particles are flowing from one control valve to another control valve, and where it is collection is taking place with this kind of picometer, you can able to get true density of your powder particles to measure the true particle densities. And this is what the Hall flow meters which we are using generally for the all flowable powder particles. Which are not flowable, we are using Carney flow meters. And if you see the spherical, irregular and flake. If powder particles are very spherical, its apparent density is 4.5 and its tap density is 5.3. How do we define this apparent density and tap density? Why we are having variations in these things? If it is irregular, 2.3, 3.14, and the flake 0.4 and 0.7. Why we are having these changes? The apparent density, how do we measure? We know with respect to the mass of powder particles, that is what 50 gram, and volume of your container, how much powder particles it is contained, mass by volume. Then why the tap density is higher than the apparent density? Because we are applying pressure, tapping onto your powder particles, then it will compact more, then it will voids are going to be very less. We are compacting more amount to remove the voids. That is what applying pressure, it will increase the density of your particles. That will give higher density than in all the spherical, irregular or the flake-like structures. If you are having a flake-like structures, the apparent density is low because it will create more amount of voids, more amount of empty spaces. That is going to have the less apparent density and all, comparing with your spherical powder particles. That is how you can think of the apparent density with respect to size distribution and as well as tap density. Tap density will give us increasing the density of the powder particles. And if you see now we are coming to the sustainability. Till now we talked about characterization, powder manufacturing, how do we qualify the powders for additive manufacturing aspects. Then it comes to the recycling characteristics. That recycling will going to affect the size, roughness, surface oxidation, and as well as moisture contamination and agglomeration. All these properties are going to affect your flowability and good packing factors or the packing density. Okay. And if you see that powder degradation also will takes place. If you cannot store the powder particles like that, because if you take the powder particles and keep it for 5 years, and again if you use same powder particles for additive manufacturing, then what will be the problem? Can you use that kind of a storage of powder particles? Yes, for ferrous based materials, and if it is a non-ferrous materials, we cannot able to store such like that, because it will contaminate, it will oxidize, or it may be impurity or foreign particles may be contaminated, and even during transportation it may be contaminated. That is why we need to think of how degradation, will that deformation or oxidation or dealloying or sintering or wear or fragmentation or oxide deposition, because once we use the powder particles, all these come across in a picture. Your powder particles once we use for printing inside even our vacuum chamber or in the argon atmosphere, it will be come across with all these process parameters. because your molten pool is surrounded with the powder particles. That powder particles are going to affected by heating or by the molten pool bath or by the energy sources or by the fluid dynamics interactions. Because of these things, your reusing of powder particles should be very, very careful. Some of the studies have undergone this reusing of the powder particles. How much extent we can able to reuse? Even we have studied lot of aspects in what extent we can reuse the powder particles, either titanium or stainless steel or some other stainless steel based materials, martensitic or austenitic materials and all. And if you see that this is the highly spherical powder particles, fractured powder particles, deformed powder particles, irregular, satellites and as well as melted. There is a different size, different morphology of powder particles, right? In these things, if you see, the original powder particles is E, right? Because that does not fracture, does not deform, does not having any sphericity, right? If you use these kind of powder particles, or if you are using some kind of recycled powder particles, what is the volume fraction? If you see the powder size and as well as the distribution, recycled one and the original powder, red one is original and the black one is the recycled one, means the size distribution is changed. Why the size distribution is changed? Because it may be agglomerated or it may be contaminated with these kind of satellites, or it may be fractured or it may be deformed. Because of all these things, your recycled powder particles changing the distribution sizes. Okay? And if you see, this is what the recycled powders, this is what the original powder particles. Because so much of satellites are there, so much of agglomerated particles are there. If I use these kind of powder particles, then what is the things, what is the porosities, what is the mechanical properties we are going to come across? If you see that the powder particles, recycled powder particles and the original powder particles, the porosity diameters inside our particles, the pore diameter is very, very high, the count number is very high in the recycled one, but in the original one, the porosity and the pore diameter and the count is very, very less and all. Because this will also going to create and the oxygen contamination. If you see the original powder 200 to 250 ppm, but in the used powder almost 300 to 350 ppm level, the oxygen contamination is increasing. If you use these kind of powder particles, then we are come across with the poor mechanical properties. And if you see, if I use these kind of the reused powder particles, what are defects we are going to come across? Either porosity, distortion or roughness or cracks or maybe inclusions or delaminations or maybe straining, going to create all these poor mechanical properties and more amount of residual stresses in the printed part and all. That is why we need to think of how many number of reuse cycles to get the repeatability in the part printing. One of the study people have done to reused powder particles and as well as the original powder particles with the stainless steel materials, and they have come across with the alloy also. If you see, this is the original printed powder particles and with the reused powder particles, if you see the porosity level is 0.4%, and if they use reused powder particles, they end up with 1.47%. This is what with the X-ray CT data and with the optical micrograph. With the optical micrograph, we cannot see much differences. We can see the melt pool, we can see the porosities at different locations, but when you see that porosity in the volumetric, you can able to come to know the porosity level is increased in the reused powder particles. That is what, if you see the volume of porosity is increasing with respect to the defect diameters. And if I check this, the volumetric porosity, if you see that recycled powder volumetric porosity is very, very high. And if they use the mechanical properties of that recycled powder, if you see that original powder will have the more amount of ductility properties, elongation properties, then the recycled one is poor elongation properties, and it is matched with your more or less same of the yield strength and the tensile strength. This is because the powder particles are oxidized and then if you see that the fractographic images of that powder particles, more amount of the cracks and the delaminations or voids can be observed in the recycled powder particles comparing with the original powder particles. This is the causes for your decreasing mechanical properties as well as ductility of the part and all. But if you are not knowing who is the supplier for our powders, then we are not going to compare our the quality of the printed parts with respect to the certifications and all. That is why we have to make sure the powder particle should be original and has to be highly qualified for AM. Okay. The another part people have done with the 17.4 pH and all. As I told, the properties are going to affect porosity, distortion and as well as straining and delaminations. If you see here, what happened here? The original and as well as the reused powder, it has got deformed. The part has got deformed because they are used a reused powder, and that reused powder are going to create deformation in the printed part because of the more amount of the straining is taken place in the printing. Because we are supplying more amount of energy, either maybe because of oxidation or to melt or to minimize the porosity levels and all. Because of that, it is going to create deformation in the parts and all. If you they have analyzed in depth to understand why that deformation, what kind of defects are going to come across in the reused powder particles. If you see, they have analyzed with the temp, then that oxide inclusions in each layer they can able to observe. If you see, this is the one layer, multiple layers, in each layer they can able to see and understand the oxide inclusions in each layers. Because of this oxide inclusion, you can able to end up with the difficulties or different accident contaminations in your printed parts. Is what oxide inclusions they have understand with the mapping, with the EDS mapping. You see these dark patches of all the oxide inclusions which are come across in the printed parts. This will give a poor mechanical properties in the ready to manufacture parts and also create these kind of the porosity and all. Thus is caused for your poor ductility. If you are having more amount of porosity, then automatically the ductility will be very low. Because of that, you can able to see, understand. Then now if you think of the sustainability impact drivers for metal additive manufacturing, we are talked how much reuse of your powder particles, 4 times or 10 times or 15 times. If I use 4 times, what will happen? If I use 2 times or if I use even after saving, will be directly you are using recycled powders for additive manufacturing, either LDD or PBF process. Yes, we can use even up to 4 times, but we are end up with these kind of problems, either the inclusions or variations in the ductility properties or the strength properties. But if you think of the wastage in the DD process or in the PBF process, if you see here the 60% wastage will be there. But when you think of these things with respect to binder jet or EBM or with the SLM solution or with the PBF process, if you see the how much amount of the energy efficiently requirement with respect to the process rate, means the electricity or the energy which is required 8.3 e to the power of 7 joules per kg is required in the binder jet process, 6.1 in SLM or the PBF process or in the DMLS system. In the EBM we are using less energy requirement, that is what 1.1, more than that the SLM and the binder jetting we are using. This is how we need to understand how much the energy requirement, that is what the cumulative energy demand is required with respect to the different processes and all. That is what the power or the energy intensity or the production rate of our powder comparing with your conventional manufacturing process. Is that really the suitable for our the application aspects and all. The one way how we can make it sustainable means how much quantity of your powder particles using, how much energy we are using, and what is the carbon dioxide emission, and how much amount of argon gas we are using comparing with your conventional manufacturing process. We need to quantify how much topologically we are redesign, means if part is complex, then we need to go for multiple manufacturing process in conventional, multiple scenarios, multiple assemblies, welding or fixture or with rivet joints or with assemblies are required. But in AM we can go with a single process, but how much energy is required in terms of gas or in terms of powder, in terms of machine, in terms of post processing and all, we need to calculate, and then we can think of how sustainable it is. That is what we need to know. Data is available in this sustainability aspects, but we need to think of how we can able to quantify in terms of sustainability aspects and all. That is what we need to think of, whether we are using recycled powders or whether we are using original powder particles and all. That is what with 4K and 6K additive solutions, they have started developing powder particles with recycling. Means they are collecting all the powders from the users. Those are the users, maybe industries or from the academia. They are collecting the powder particles, used powder particles. Even though after they are used 2 times or 4 times, rest out powder particles is contaminated, is oxidized. Those powder particles they are collecting to the industry, then they do receiving, then they go for some kind of the removing of impurities, then they are producing the powders again like a original powder particles. If you are using like these kind of powder particles, then it is more. That is why we need to think of, even people are doing with your some of the scraps, whether we are using machined materials. Even 6K is 6K additive solution, they are also using machine scrapping. By turning or milling, if you do the machining of any material, they will collect all these chips and then they will collect in terms of a tons. Then they use that all the chips to be contaminated, because you are using so much of coolants, it may be contaminated, oxidized because of the heat affecting during machining and all. Then we have to clean all these aspects by impurities and removing all these oxidations and contaminations. Then they will melt it again, then they will produce the powders. Instead of going for the original powder manufacturing, you are using the scrap from the conventional, that can be used for making the powders. That is more sustainable than the original usage in the additive manufacturing. That is how we need to think of how the powders are produced, but will that giving a same quality aspects in terms of the reproducibility or the mechanical properties and all. That is also we need to think of in terms of sustainability aspects. 6K has started even the support structures, because when we print metal parts and in PBF process or in DD process, we are providing so much of support structures. Wherever we are having overhanging structures, we need to provide support structures. Then what is the waste of these support structures? Because support structures we are providing in different simple designs and all, just to hold that overhanging which is possible for the painting. Even in the EBM, so much of the stuck powders or the agglomerate powder particles will be there. These are all like acts as a support structures. All these powder particles can be a raw material for your powder productions or the chips. All these the rejuvenated powder particles, agglomerated powder particles, can make use of the premium the powder particles with the plasma automation or with the vacuum induction automation process. With that, 6K has developed these kind of support structures or this kind of unused powder particles or part which is already broken or it may be deformed during printing, it may be failed. All these they have done collection from the industries as well as from the academia to produce the powder particle. That is what the failed powder particles, failed builds, support structures or condensates, or it may be primary ingots, or it may be reuse of partially melted powder particles, or the machine turnings, or the end life of the powder particle. All these things they can collect it to make these kind of the premium powders by the plasma automation process and all. That is how they can use these kind of powder manufacturing. If you see, initial process is what? If you are using a chips and all, these kind of turning chips or milling chips and all, then we can use these kind of simple chips by the mechanical milling, ball milling process. We can use to produce these kind of the powder particles as a, this is not spherical but somewhat nearer spherical. such kind of powder particles we can make use by your ball milling process. Chips are converted into a powder particles by mechanical attrition. Even mechanical attrition we can use, tumbler milling we can use, this kind of ball milling we can use to produce this. These raw materials can be used as a input for your plasma automation or for the gas automation techniques. That is why we can use. This is what the methodology to clean and prepare your machining chips, because we cannot use directly these chips for producing, because it may be contaminated with your coolants, or it may be oxidation, or it may be some other impurities and all. That is why we need to clean that powder particles. For that we have to follow these processing stages after the machining chips and all. Whatever the coolant impurities we need to clean with water, with other solvent solutions, and then what are the detergents or ethanols or acetones, isopropylene alcohols we can use to clean it, or it may be worn out from the tool contaminations. Tool may also worn out contaminated in the chips and all, that also has to be cleaned, and then we have to use that recycled one for making the powders by the mechanical processing. This is what the flow chart we need to follow for making the powders by the machining chips and all. And once if you are following all those aspects, we are using that powder agglomerated powder particles to make the very spherical powder particles with the vacuum induction automation or plasma automation process. That is what, if you see the regenerated nickel powders 6K additive solutions have proved to sustainability in these powders. Means worldwide they are the leading manufacturers nowadays. The used powders they are buying and they are selling in a minimal cost with this kind of the powders, because this will be very equivalent to your original powder particles. That is what, highly spherical powder particles, and they are more flowable properties, very good compaction, very good apparent density, and all the aspects are required in these powders. That is possible by the automation techniques. With the rejuvenation we can able to do it. And even if you see these kind of chips, recycled scraps, machining or 3D superstructures or scrap from the 3D parts are used, that can be used by the low cost mechanical pre-alloying or mechanical processing. Then we can use that low parts or with different kind of processes, EBM or PBF or LDD or with binder jetting. All these things can be used for making a high quality powders by adapting the sustainable sources. These are all the sources for making the powders instead of using a original powders from the ingots and all. And if you see that quality, then how do we assure that these kind of powder particles are quality assured? Then that 6K solutions has maintained the quality aspects in terms of characterizing all the properties, start from first to flowability, morphology, sphericity, and then how they can able to clean it, and how they can able to engineer into a feedstock, and then how they can able to spherodize to produce the highly quality powder particles. Then they qualified that printed parts with the original powder particles to qualify repeatability in the original powders and the reused powders. This is how we can make use our sustainability aspects in your powder manufacturing. That is powders how we can use for our additives also. From this takeaway, if you see the summary of these aspects, we can adopt even nowadays the machine learning techniques, because we are producing the powders, but will that having some kind of the technological adaptment. We do not know how machine learning based techniques are efficient for framework in developing this automation things. None of the people have adapted this machine learning techniques for adoption of the powder automation. One can apply that kind of the machine learning techniques to powder manufacturing, powder productions and all. And another one is a use of real model with identifying the optimal production conditions while accounting for the real world constraints and all, because we have lot of constraints in the powder manufacturing. That is what in situ monitoring, how we can improve the yielding effective or automation, because yielding is very low in your automation. How we can able to improve that yielding of your automation? That's one way I can think of. How improve the sustainability through the efficiency, gains and renewable energies, and integration and scrap material utilization. We can reuse all the scrap materials instead of throwing into the environment. We can reuse all those things and we can use it for a raw material for the powder productions and all. And promote powder recycling as a key component for the circular economy. We have to promote in all the Asian or European sector recycling of these powder particles. Then you can able to use as a circular economy for our powder productions and all, and reduce the carbon emission and energy consumption through this coordination effort across this overall AM workflow. Then only you can able to minimize our the environmental impact of your powders or the additive manufacturing on the society. That is what we can minimize gas house emission effect and all, and also recognize the critical importance of the powder sustainability in terms of the powder bed fusion process, because in powder bed we are almost 60% of powder wastage will be there, because the entire build area we are not going to build, it is not a complete a solid block, it will be of depending on the structures, then support structures we have to provide, almost 60% wastage will be there. Then we need to think of how critically powder sustainability can be done in PBF aspects, and emphasizing the recycling, resources conservation, as well as the fundamental achieving the sustainability in the additive manufacturing aspect. These are all the things we need to understand to apply our sustainability in our additive manufacturing process. But all these things cannot be applied, but there should be a trade off between the sustainability aspects and as well as additive manufacturing. Means even all the quality powders in terms of PBF process, what is the binder jet process, or with respect to multi-material additive manufacturing. Even multi-material it will be difficult. If you go with the copper or nickel based alloys, copper with stainless steel alloys, it will be contaminated copper as well as steel. Then again we have to separate out with the density aspects and as well as with the chemical aspects. Then it will be a more tedious process for sustainability aspects of such kind of functional grade materials, multi-materials. There is a trade off between these sustainability and as well as with respect to the additive manufacturing aspects. Okay. With this I will conclude. If you have any doubts or clarifications, you can write to me or you can require, I can able to answer your queries. Any doubts? Or you are tired? Too much? No queries? Okay. Okay, then we can end the session here. Okay. We will start again tomorrow morning, and hopefully from tomorrow onwards afternoon will be a lab session. Okay. We can take you to the lab and as well as some modeling aspects. We can train you on the simulations as well as end topology and all those things we can learn from tomorrow onwards. Okay. Thank you.